For as long as we've looked up, we've asked a simple question. If life found a way here, why wouldn't it find a way out there? The strange thing is, we know almost nothing about those places. We've never seen an alien ocean ripple under another sun, never watched clouds swirl on a distant world in a foreign galaxy. All we see are faint smudges of light, tiny blurred stamps on the fabric of the night. But hidden inside each smudge could be billions of stars, billions of worlds, billions of attempts at life, maybe even billions of failures. So tonight we step beyond the Milky Way, not with a spaceship, but with a question. What are the real chances that life exists in other galaxies? And what would it mean if the universe has been alive in more places than we ever dared to imagine? This is where our journey begins. Before we wander too far into the cosmic ocean, we need to confront a simple but crucial truth. Life, as extraordinary as it feels, is built from some of the most ordinary ingredients in the universe. This is one of the most important keys to estimating the chances of life in other galaxies. If life were made from exotic particles, rare elements, or impossible chemistry, then the vast majority of the universe would be sterile by default. But the deeper we look, the more evidence we find that the building blocks of biology are not a local accident. They are everywhere. Pick up a handful of soil from your garden, a pinch of dust from under your bed, or a sliver of rock from a mountain. Almost everything in your hand, carbon, oxygen, nitrogen, iron, silicon, was once forged inside a star. These elements were not created on Earth. They were not even created in the Milky Way alone. They have been drifting through space for billions of years, cycling through generations of stars and galaxies, like ingredients in a recipe repeated over and over throughout cosmic history. And as strange as it sounds, we've seen these ingredients far beyond our galaxy. Telescopes like Hubble-ALMA and JWST have detected carbon-bearing molecules, complex organic compounds, and even water vapor in galaxies so distant that their light began travelling toward us before the sun even existed. In other words, the universe was mixing the chemistry of life long before life appeared on Earth. At the heart of this universal recipe is carbon. Carbon is a strange and versatile element with a gift that borders on magical. It can form long, stable chains that then fold and twist into an almost infinite variety of structures. No other element does this as well. These structures become the backbone of amino acids, proteins, and DNA, the machinery of life. And carbon is everywhere, woven into interstellar dust, clinging to asteroids, swirling in molecular clouds, drifting between the stars of distant galaxies. If you travel to the far side of the universe, the carbon you breathe there would behave just like the carbon in your body right now. Next comes water, the universal solvent, the gentle medium where chemistry can move, collide, and evolve. Water is abundant on Earth, but it is not an earthly treasure. Astronomers have found water in the atmospheres of exoplanets, in the tails of comets, in the icy moons of Jupiter and Saturn, and in giant molecular clouds thousands of light years wide. They have even found water signatures in galaxies billions of light years away. Wherever you find star formation, you tend to find water. Wherever you find cold clouds of dust, you often find ice. The universe appears to manufacture the tools of biochemistry as casually as a storm cloud makes rain. But chemistry alone is not enough. Life also requires energy, not too much, not too little. A planet needs warmth to liquefy water, but not so much that molecules are torn apart by radiation. It needs light or heat or chemical gradients, and it needs a stable environment that lasts long enough for simple molecules to learn how to copy themselves. On Earth, this took hundreds of millions of years. In the cosmic timeline, that is a blink. But for chemistry to repeat the experiment elsewhere, it needs a world that remains calm for long stretches of time. This raises a deeper question. Are these conditions common in other galaxies, or are we living in a rare pocket of stability? Galaxies are complex ecosystems. Some are too young to have built many heavy elements. Others are too violent with frequent supernovae and intense radiation. Some are quiet but starved of material. The universe is diverse, and not every corner of it offers a friendly environment for biology. But even if only a small fraction of galaxies have long-lived stars, stable regions, and a rich reservoir of heavy elements, the sheer number of galaxies means we are dealing with enormous possibilities. Let's look at this through a more grounded lens. If you stripped the Milky Way of all its stars and looked only at the kinds of gas and dust it contains, you would still find the same chemistry that we detect in galaxies far away. There is nothing in our galaxy's chemistry that appears unique or magical. The molecules that eventually assembled into DNA here could have assembled into something similar elsewhere. The water that fills our oceans is indistinguishable from the water vapor we detect in distant galaxies. In every direction we look, the universe repeats the same patterns. This is the part that changes everything. The origin of life on Earth may have been improbable, maybe even astonishingly unlikely, but the ingredients were not. They were abundant. They were ancient. They were shared across the entire universe. So when we ask about the chances of life in other galaxies, we are not asking whether the universe has the right ingredients. It clearly does. We are asking something deeper. Under the right conditions, will those ingredients inevitably fall into place? Does chemistry naturally climb toward complexity? Or did Earth experience a freak accident of cosmic luck? We cannot answer that question with certainty, but we can say this. If life requires carbon, water, and time, then galaxies across the universe possess all three in staggering quantities. And if life requires countless random events to align perfectly, lightning strikes, tides, volcanic vents, stable climates, then galaxies provide billions of planets where these events can play out. Life then is not a miracle tied to one world. It might be a natural consequence of a universe that is full of opportunities. And if that's true, the chances of life in other galaxies do not just rise, they explode. They multiply. They turn from a low probability into a cosmic inevitability spread across 1 trillion star systems in 1 trillion separate galaxies. But before we jump to conclusions, we need to understand the engines that make life possible. The galaxies themselves, what are they really? How do they create stars, planets, and heavy elements? And why would some galaxies be better homes for life than others? To answer those questions, we must travel deeper into the structure and behavior of galaxies, the vast factories that turn darkness into light and chaos into possibility. The next step of our journey begins with a simple idea. What is a galaxy truly when you look past the light and into the physics that holds it together? When we look at a galaxy from afar, it feels almost unreal. A glowing whirlpool of light, a delicate smear across the void, a cosmic pinwheel frozen in slow motion. But galaxies are not fragile things. They are colossal structures built from gravity and time, spanning tens of thousands to hundreds of thousands of light years. They are engines, ecosystems, factories, and for our purposes they are potential homes. But what is a galaxy stripped of the poetry and reduced to its bare components? At its core, a galaxy is a gravitational community, a bound collection of stars, gas dust, dark matter, and the remnants of stars that lived and died long before Earth was even a dream. Every galaxy contains generations of history layered on top of one another. Every photon of light we see from them is a message from a star, and every star is a chapter in a much older cosmic story. Let's start with the stars, because they are the beating heart of any galaxy. Each star is a nuclear furnace, a sphere of plasma where hydrogen fuses into helium, releasing light and heat. Stars are born from cold clouds of gas and dust that collapse under their own weight, igniting when the pressure in their cores becomes unbearable. And once they are born, they begin the long process of enriching the galaxy around them. They manufacture heavy elements in their cores, then release those elements during their death throes in shimmering planetary nebulae or catastrophic supernova explosions. Without these cycles of birth and death, galaxies would remain chemically primitive. They would lack carbon, oxygen, nitrogen, iron, the essential ingredients of life. Surrounding these stars is dust, tiny grains of carbon, silicon, and metals that float like smoke in the vacuum of space. Dust may sound insignificant, but it is a key ingredient in building planets. Without dust you cannot form rocky worlds, icy moons, or the complex molecules that cling to their surfaces. Dust is where chemistry happens. Dust clouds are where molecules form, evolve, and eventually become the seeds of life. Yet galaxies are not held together by stars or dust. The true skeleton of a galaxy is made of something invisible and mysterious: dark matter. We cannot see it, touch it, or interact with it directly, but we can feel its influence in the way galaxies rotate. Without dark matter, galaxies would tear themselves apart. Their stars spin too fast. Their luminous mass alone is not enough to hold them together. Dark matter forms a vast invisible halo around each galaxy, a gravitational container that shapes the galaxy's structure and controls its evolution. Inside this dark matter, halo stars and gas swirl together in patterns determined by the galaxy's type. Spiral galaxies like our Milky Way have elegant arms that wind outward from a bright core rich with dust and continuously forming new stars. Elliptical galaxies are more like giant stellar clouds, smooth and featureless, with little gas and few newborn stars. Dwarf galaxies are small, irregular, and easily disturbed by their larger neighbours. And then there are galaxies twisted by collisions, torn by gravitational tides, or inflamed by bursts of star formation so intense that their light outshines entire clusters. The diversity is breathtaking, and each type of galaxy creates a different environment for planets and life. Spiral galaxies, for instance, are fertile. Their arms are full of cold clouds where stars form in dusty nurseries. The balance of old and young stars provides both heavy elements and long-lived stability. Galaxies like the Milky Way or Andromeda are often considered strong candidates for housing complex life. Their structures offer wide, quiet suburban zones where radiation levels are moderate, and conditions remain stable for billions of years. Elliptical galaxies are quieter, older, and often poorer in gas. They no longer form many new stars, but they contain enormous numbers of old ones. Stars that have been shining steadily for billions of years. Some astronomers argue that elliptical galaxies might actually be excellent homes for life, not because they are fertile, but because they are peaceful. Their low rates of supernova explosions mean fewer catastrophic events that could sterilize planets. Irregular and dwarf galaxies are more chaotic. They are shaped by gravitational interactions, collisions, or bursts of star formation that flood their environments with radiation. Some may be too unstable for life to persist long enough to reach complexity, but others may contain small pockets of stability, quiet corners where life could slowly develop in isolation. The important point is this: galaxies are not just collections of stars. They are dynamic environments shaped by physics, history, and chance. Their structures determine how many stars they form, what kinds of planets those stars can sustain, and how often catastrophic events threaten to wipe life out. When we think about the chances of life in other galaxies, we must think about galaxies the way a biologist thinks about ecosystems. Some are jungles teeming with activity. Some are deserts. Some are burned forests recovering from ancient fires. Some are frozen landscapes waiting for the first signs of spring. And yet, despite their differences, galaxies share one remarkable trait. They all operate by the same physical laws. Whether you're in the Milky Way, the Virgo cluster, or a galaxy at the edge of the observable universe, the same processes unfold. Gravity collapses clouds into stars. Stars forge elements. Elements gather into planets. Chemistry begins its slow dance toward complexity. The universe does not play favourites. It uses the same rules everywhere. This universality is our great clue. It suggests that if life could emerge here in a quiet arm of an average spiral galaxy, then the potential for life is woven into the very nature of galaxies themselves. The question is not whether galaxies can host life. It is which galaxies are most likely to create the right conditions and how often those conditions occur. To answer that, we must dive deeper. We must examine how stars are born, how they die, how they enrich their galaxies with the ingredients of life, and how different galactic environments influence the stability required for biological evolution. Because galaxies in all their beauty and violence are not just backdrops to the story of life, they are the stage on which the story begins. Our next step leads us into the fire. How do galaxies forge the stars that make life possible? To understand the chances of a life in other galaxies, we must start where every world begins. Inside the cold, dark womb of a collapsing cloud of gas, star formation is not gentle, it is not peaceful. It is a slow, crushing struggle between gravity and pressure, a cosmic ballet that has played out trillions of times in galaxies across the universe. And wherever stars are born, planets follow. And wherever planets form, the door to life cracks open, even if only slightly. Picture a galaxy's spiral arm. Not the glowing blue arc seen in photographs, but the vast sprawling structure itself. Hidden inside it are molecular clouds, titanic structures of hydrogen, helium, dust, and trace molecules. Some of these clouds are hundreds of light years wide, dense enough to block starlight entirely. If you could drift inside one, you'd find yourself surrounded by darkness so deep that even nearby stars would vanish. It is inside these shadows that new suns begin their quiet descent into existence. Gravity pulls the cloud inward, squeezing it tighter and tighter until it fragments into smaller pockets. Each fragment begins to collapse under its own weight. As the material gathers, it heats up. This heating continues until the core becomes a protostar, a spinning sphere of gas not yet hot enough for nuclear fusion. Around it forms a disk of swirling dust and debris, the beginning of a planetary system. What makes this process so important is its universality. Whether you're looking at a star-forming region in our Milky Way, or in a galaxy billions of light years away, the same physics applies. The rules don't change. Gravity behaves the same, gas behaves the same, dust behaves the same. And when the process finishes, the result is familiar. A star surrounded by a disk of raw materials ready to assemble into planets. But the story doesn't end with starbirth. It only begins there. Newborn stars often come in clusters. Some clusters form dozens of stars, some hundreds, and the most colossal can form tens of thousands. These newborn stars vary wildly in size and temperature. Some are small, dim red dwarfs that will burn quietly for trillions of years. Others are enormous blue giants destined to live fast, die young, and explode in spectacular supernovae. This diversity matters. Smaller stars give life the luxury of time. Larger stars return the heavy elements needed for life back into the galaxy. The cycle repeats endlessly. Stars form, shine, die, and seed the galaxy with carbon, oxygen, nitrogen, iron, phosphorus, all the elements required for biology. Without this cosmic recycling, galaxies would remain barren deserts filled only with hydrogen and helium, but thanks to generations of star birth and star death, galaxies become enriched with the materials that eventually form oceans, atmospheres, continents, and living cells. The regions where stars form are therefore critical to understanding whether a galaxy can host life. Spiral galaxies like the Milky Way, with their dense arms and abundant gas, are especially productive. Their structure funnels gas into narrow lanes where compression triggers star formation. The spiral arms rotate, slowly sweeping star-forming clouds through cycles of density that create new generations of stars. This constant renewal fills the galaxy with fresh elements and fresh opportunities for planets. Other galaxies behave differently. Elliptical galaxies, for example, are largely retired. They formed most of their stars long ago and now contain mostly old metal-rich stars, but very little gas for new stars to form. Without gas, there are few new planetary systems, but there may be many ancient worlds orbiting long-lived stars. Whether this environment is good or bad for life depends on how long stability must persist. More chaotic galaxies, dwarfs, irregulars, or those caught in collisions tend to form stars in bursts. In these galaxies, star formation can be violent and erratic. For every star that forms peacefully, another may be born in a region racked by radiation, shock waves, and turbulence. The same supernova explosions that enrich the galaxy with the ingredients of life can also sterilize nearby worlds, stripping away atmospheres and interrupting evolutionary progress. And yet even in these galaxies, pockets of calm can exist. The universe rarely paints with only one brush. Regions of violence can sit alongside regions of tranquility. In some dwarf galaxies, astronomers have found long-lived stars with planets that appear surprisingly undisturbed. In others, star-forming regions stretch across vast swathes of space, raising the tantalizing question, could these unstable galaxies still produce the seeds of life? Across all these environments, the fundamental truth remains. Stars are the factories of everything life needs, and star formation is not unique to the Milky Way. It happens everywhere in every corner of the universe where gas and gravity interact. The chemistry that leads to life is not a rare trick. It is a natural consequence of a universe filled with stars that are constantly born, constantly die, and constantly renew the cycle of creation. Think of galaxies as ecosystems. The rate of star formation in a galaxy determines its character, whether it is fertile, barren, chaotic, or serene. A galaxy with a rich supply of cold gas is a vibrant forest full of new growth. A galaxy stripped of its gas is a desert of aging stars. A galaxy caught in tidal interactions is a storm-tossed ocean, difficult for stability but full of energy. And a galaxy with slow, steady star formation like the Milky Way is a balanced landscape, neither too violent nor too stagnant. This balance may be key. The Milky Way's moderate star formation rate, its abundance of heavy elements, and its wide, quiet suburbs have likely played a central role in nurturing life on Earth. If life requires both diversity and stability, then galaxies like ours may be the perfect middle ground, not too mild, not too dangerous. But to understand why some galaxies are better suited for life than others, we must look beyond star formation itself. We must examine the ingredients that stars produce and how these ingredients shape the planets that form around them. Not all galaxies have equal access to these elements. Some are rich with heavy metals, others are poor. And this matters deeply because the birth of a planet, especially a rocky world like Earth, depends on having the right materials in the right amounts. So our next step is to confront the chemistry of galaxies on the largest scale imaginable. How does the metallicity of a galaxy shape its ability to form worlds like ours? If stars are the engines of creation, then the elements inside them are the currency of life. Hydrogen and helium may make up most of the universe, but they alone cannot build a world like Earth. For planets to grow solid surfaces, build mountains, form oceans, and support biology, they need heavier elements: carbon, oxygen, nitrogen, iron, silicon, phosphorus, sulfur. These metals, in the language of astronomy, are called metallicity, and the metallicity of a galaxy tells us something profound. How ready it is to build rocky planets, and therefore how ready it is to build potential homes for life. The word metallicity sounds technical, but the idea is simple. When the universe first burst into existence, it created only the lightest elements. The heavier ones didn't arrive until stars formed and began fusing matter in their cores. Each generation of stars enriched the cosmos a little more. By the time our solar system formed 4.5 billion years ago, previous generations of stars had already created enough heavy elements to build a rocky planet with continents, oceans, and a complex climate. But this raises a question. If heavy elements are required for rocky worlds and heavy elements take time to accumulate, then how many galaxies are actually old and rich enough to have had a fair shot at forming Earth-like planets? The answer depends on how stars live and die across the universe. Galaxies with high metallicity have experienced many cycles of star birth and star death. They have been cooking the ingredients of biology for billions of years. Their molecular clouds are full of dust enriched by older stellar generations. These galaxies are like mature kitchens stocked with everything needed for a diverse recipe. The Milky Way is one of them, with billions of years of stellar evolution behind it. It offers a rich inventory of metals enough to form countless rocky planets, icy moons, complex atmospheres, and maybe even oceans under alien skies. But some galaxies are young, chemically primitive, and still building up their supply of heavy elements. In these places, the cosmic kitchen is sparse. Rocky planets might be extremely rare or small. Worlds made mostly of gas, ice, or water may dominate. These galaxies might produce fewer biological opportunities simply because they lack the materials to build complex surfaces where chemistry can take root. Now imagine other galaxies older than the Milky Way with even more generations of stars contributing to their chemical richness. Elliptical galaxies, for example, often contain enormous numbers of ancient stars. Their lack of gas means they form few new stars today, but their long history of stellar evolution has produced a high metallicity environment. Many astronomers believe that elliptical galaxies might be treasure troves of rocky planets, orbiting stable, long-lived stars. But metallicity is not evenly spread. Even within a single galaxy, some regions are more fertile than others. In the Milky Way, the central regions tend to be richer in metals, while the outskirts are more primitive. The metallicity gradient tells us that where you are in a galaxy can matter as much as which galaxy you are in. To build life, you need the right star in the right neighborhood at the right moment in cosmic history. This diversity extends across the universe. Spiral galaxies like ours typically offer a good balance, active star formation, plus a healthy reservoir of heavy elements. Dwarf galaxies, by contrast, often struggle with metallicity. They are small, easily disrupted, and form stars in bursts. Their limited mass and frequent interactions with larger galaxies prevent them from holding on to the heavy elements produced by stars. Much of this precious material can be blown away by supernova winds before it ever settles into planet-forming clouds. As a result, dwarf galaxies may host few rocky worlds and therefore fewer chances for life to emerge. Irregular galaxies shaped by collisions or gravitational tides have chaotic metallicity patterns. Some regions are rich, others barren. Some may form rocky planets in abundance, while others remain trapped in early cosmic chemistry. These galaxies are inconsistent, but inconsistency doesn't eliminate possibility. A single stable region in an otherwise turbulent galaxy might still nurture life if it maintains a long enough window of calm and has enough metals to build complex worlds. Elliptical galaxies with their aged stars and high metallicity might seem ideal, but their quiet nature comes with a trade-off. They form few new stars, meaning fewer fresh planetary systems. Yet the planets already formed there billions of years ago could have been growing life while Earth was still a molten sphere. The idea is staggering. If elliptical galaxies host stable ancient worlds, then some of the oldest life in the universe might not be in spirals like the Milky Way, but in these quiet, red-tinged giants. All of this leads to a crucial insight. The chances of life in other galaxies are linked to the cosmic distribution of heavy elements. A galaxy's metallicity is a measure of its biological potential. High metallicity galaxies are fertile ground for rocky planets and complex chemistry. Low metallicity galaxies are sparse, offering fewer stable surfaces where life might begin. And galaxies with uneven metallicity patterns offer patchwork environments, some barren, some promising. But we must be careful. Metallicity is not destiny. Life may not require Earth-like continents or even Earth-like environments. There are entire families of worlds, ocean planets, icy moons, subsurface oceans beneath thick layers of ice that might support biology, even without high metallicity. Life could arise in places where rocky surfaces are buried beneath kilometers of water and ice. In such cases, metallicity matters less than energy, chemistry, and time. The universe is creative, and so is life. Still, if we are searching for conditions most similar to Earth, stable surfaces, complex geology, dynamic climates, metallicity becomes one of the most important filters. It helps us identify galaxies that are chemically mature enough to offer environments familiar to us. And this matters because understanding familiar environments is our first step in understanding unfamiliar life. As we continue this journey, metallicity leads us naturally to the next question. Even if a galaxy is rich in heavy elements where inside that galaxy can life truly thrive, Not every region is safe. Some are too violent, some are too sterile. Some are too unstable or too exposed to cosmic hazards. To find the real chances of life in other galaxies, we must now zoom inward into the structure of galaxies themselves and discover the hidden geography of survival. Our next step brings us face to face with the surprising concept, the habitable zones of galaxies. When we talk about life in the universe, we often begin with something small, a single planet, a single star, a narrow ring of space where temperatures allow liquid water to exist. Astronomers call this ring the habitable zone, the Goldilocks region. Not too hot, not too cold, just right for oceans and chemistry. But when we pull back and look at an entire galaxy, something surprising appears. Galaxies also have regions that are friendly to life and regions that are not. These are the galactic habitable zones, and they matter just as much as the habitable zone around a star. A galaxy is not warm like a star. It does not create a single bubble of heat, but it creates environments, wide regions shaped by radiation, star density, heavy elements, and long-term stability. If a planet forms in the wrong part of a galaxy, even the perfect orbit around the perfect star might not save it. So what makes a galactic region safe? The answer begins with stability. Life needs calm conditions that last for billions of years. Evolution takes time. Chemistry needs peace. Near the center of a galaxy, peace is almost impossible. Most galaxies have a supermassive black hole in their core. When these black holes feed, they release intense radiation. They fire jets of plasma. They flood nearby space with X-rays and gamma rays. The region around the core is also packed with stars, so packed that supernova explosions are common. Too much light, too much energy, too many disasters. This inner region is dangerous. It is bright. It is crowded. It is unstable. A planet here might never hold an atmosphere long enough for life to appear. Far outside the core at the galaxy's edge, the opposite problem appears. Space becomes thin and quiet. Star formation slows. Heavy elements become rare. These outer regions lack the metals needed to form rocky planets. Life may find safety here, but it may never find a good place to begin. Between these two extremes is the sweet spot, a wide region where conditions are balanced. Here metallicity is high enough for rocky planets. Star formation is steady. Radiation is moderate. Supernovae happen, but not too often. Stars have room to breathe. Orbits remain stable for billions of years. This region is the galactic suburb. Our sun lives in this suburb of the Milky Way, not too close to the center, not too far from the edge. We orbit through a calm lane of a spiral arm where the environment has stayed mild for more than 4 billion years. Earth could not have evolved in a better place. This pattern applies to other galaxies as well. Each galaxy has its own habitable geography, its own safe and unsafe regions. These regions are shaped by star density, the metallicity of each zone, the history of supernova explosions, the activity of the central black hole, and the pattern of star formation across time. Spiral galaxies like Andromeda likely have large spiraling habitable zones. Their arms create long stretches of mild conditions where planets can survive and evolve. Elliptical galaxies may have fewer young stars, but they contain billions of old stable ones. Their habitable zones may be narrower but extremely peaceful. Irregular and dwarf galaxies can be chaotic. Their habitable regions may appear in scattered pockets. Some pockets might be unstable. Others might be surprisingly calm. Even in chaotic galaxies there can be small islands where life has enough time to begin. The important point is simple. The chance of life in a galaxy depends on where a star is born, not just which galaxy it lives in. A star inside a dangerous region may face constant radiation. A star in the outskirts may never form planets. But a star inside the sweet spot, inside the galactic habitable zone, could host a world very much like Earth. And this leads us to a deeper question. If galaxies have habitable zones, then where do most stars actually live? Do they form inside the safe region or outside it? And how does this affect the overall chances of life? To answer that, we must travel into the galaxy's brightest, most violent territory, the inner core, the region that glows like a furnace and threatens everything around it. The center of a galaxy is one of the most mesmerizing places in the universe. When we look at those bright glowing cores in telescope images, they seem peaceful like the warm heart of a cosmic city. But looks are deceiving. The center of a galaxy is not peaceful at all. It is one of the most dangerous environments a planet can ever experience. And for life, it may be the closest thing to a guaranteed extinction zone. Most galaxies have a supermassive black hole in their core. The Milky Way has one too, called Sagittarius A star. It is quiet now, but it has not always been silent. When these black holes feed even a little, they release tremendous amounts of energy. They heat surrounding gas blast radiation into space, and sometimes launch jets that stretch thousands of light years. These eruptions can sterilize regions around them, stripping planets of their atmospheres or flooding entire sectors with lethal radiation. But the black hole is only part of the danger. The central region of a galaxy is crowded, extremely crowded. Imagine all the stars you see in the night sky. Now imagine packing them so close together that each one sits only a fraction of a light year apart. In the galactic core, stars live in tight clusters. They tug on one another. They disturb each other's orbits. Even stable planetary systems can be pushed off balance over long timescales. For life, long-term stability is everything. You need a planet that keeps its orbit for billions of years. You need gentle climates, steady temperatures, and enough time for chemistry to explore possibilities. But in the core, orbits do not stay steady. A passing star can pull a planet slightly closer to its sun or slightly farther away. A small change over millions of years can turn oceans into steam or into ice. Planetary stability becomes a luxury few worlds can keep. On top of all this, the core is full of supernovae. Massive stars live short explosive lives, and they are common in dense environments. When one of them dies, it floods the region with high-energy radiation. A single nearby supernova can damage a planet's atmosphere. A series of them could reset biological progress again and again, erasing any fragile beginnings before they have the chance to grow. Some models suggest that planets near the galactic core might experience sterilizing radiation events every few million years. For simple molecules that might still be manageable. But for complex life, the kind that needs deep time to evolve, these conditions are devastating. Imagine Earth's history being interrupted by violent radiation storms every time life tries to advance. You never get forests, never get animals, never get intelligence. You only get restarts. There is also the problem of cosmic rays. High-energy particles flow through the galactic center like invisible storms. These particles can break apart DNA, alter chemical reactions, and disrupt biological machinery. Even with a thick atmosphere, even with magnetic protection, a planet at the core would be under constant assault. Life might begin there, but it would struggle to last. And yet the danger does not end with radiation. The gas density near the center is much higher than in the outer regions. This gas is often hot and turbulent. It falls toward the central black hole. It crashes, collides, and shocks. Star formation happens rapidly in bursts. These bursts produce clusters of massive stars that die soon after they form, releasing more shocks and more radiation. A galaxy's core is not just dangerous. It is unstable. It is unpredictable. It is loud in every physical sense, a place where gravity, heat, and energy collide in chaotic ways. Now imagine trying to build a biosphere there. You try to form an atmosphere. A supernova strips it away. You let oceans settle. A wave of radiation sterilizes the surface. You evolve the first microbes. A nearby star wanders too close and disrupts your orbit. You try again. Something else interrupts. You try once more. Another catastrophe arrives. This cycle can continue for billions of years. It does not mean life cannot exist there, but it does mean life almost certainly struggles to evolve complexity. The conditions that allowed Earth to move from simple cells to forests and mammals and intelligence would be nearly impossible to maintain near a galactic core. Some astronomers describe the center of a galaxy as a cosmic furnace. It burns bright, but it also burns what it touches. It is a place where stars are packed so tightly that danger is never far away. Contrast that with the quiet comfort of the Milky Way's suburbs. Out here, stars drift with far more space between them. Supernovae are rare. Orbits remain stable. The black hole is distant enough that its outbursts no longer pose a major threat. This peaceful environment is one of the reasons Earth exists at all. And this difference between the violent core and the gentle outer lanes plays a crucial role in estimating the chances of life in other galaxies. A spiral galaxy may look calm from the outside, but internally it's a mix of protection and peril. The center may glow beautifully in images, but for life it's mostly a graveyard of possibilities. So if the core is too dangerous and the outskirts too empty, then life must search for the middle. The sweet region where matter is rich, radiation is moderate, and orbits are kind. But how far does the danger of the core reach? Where exactly does the no-go zone end? And at what point does a galaxy become quiet enough for life to breathe? To answer that, we must leave the glowing center behind and travel toward the silent outer regions where stars drift alone, and where danger is replaced by isolation. When we leave the violent heart of a galaxy and travel outward, the danger slowly fades. Radiation drops. Supernova explosions become rare. Stars spread out, drifting farther and farther apart. At first, this seems like a blessing, a quiet place, a safe place, a region where a fragile world might finally have the peace it needs to grow life over billions of years. But safety has a cost. And in the far outskirts of a galaxy that cost becomes clear. The outer regions of a galaxy are lonely. The density of stars drops sharply. The hydrogen and dust needed to form new stars become thin. Heavy elements become scarce. These elements, carbon, oxygen, nitrogen, iron, are the building blocks of rocky planets, atmospheres and complex chemistry. Without them you cannot build continents. You cannot build oceans. You cannot build the foundation that life needs. Astronomers call these outer regions metal poor, not because they lack literal metals, but because they lack all elements heavier than helium. In astronomy, everything heavier than helium is a metal, and the farther you go from a galaxy's center, the fewer metals you find. This is a universal pattern. Spiral galaxies show it. Irregular galaxies show it. Even ellipticals, though more uniform, still have subtle gradients. Why does this matter? Because metallicity determines a galaxy's ability to build rocky worlds. Imagine trying to form Earth in a region with only a fraction of the heavy elements we have here. The dust grains needed to seed planet formation would be rare. Rock cores would form slowly or not at all. Gas giants might still emerge because they can grow from hydrogen-rich environments. But small Earth-like planets would struggle to take shape. And without small rocky planets, the chances of life, at least life as we know it, drop dramatically. Even if a rocky planet does manage to form in these outskirts, it faces another challenge: isolation. Stars in the far outer regions of a galaxy are so widely spaced that they form no clear neighborhoods. There are fewer stellar nurseries, fewer supernova remnants rich in organic molecules, fewer comets and asteroids filled with water and carbon compounds, fewer opportunities for planets to receive the chemical diversity that helped Earth evolve. This isolation also affects star formation itself. In the outskirts, stars form slowly and rarely. Young stars are essential because they create new heavy elements when they die. But if few stars form, few stars die. And if few stars die, the outer regions never get enriched with the ingredients needed to support complex chemistry. It is a feedback loop of emptiness. Low metallicity, fewer rocky planets, fewer environments for life, fewer stars forming and dying, continued low metallicity. For life, this is not ideal, but isolation creates a second, more subtle problem: coldness. Not weather cold, but cosmic cold. The gas in the outer regions of a galaxy is faint, thin, and spread out. Without enough mass, it cannot collapse easily to form new stars. This creates vast, quiet deserts where little changes over billions of years. Time passes, Stars age, dust drifts, but nothing new grows. Life needs stability, yes, but it also needs renewal. New heavy elements, new planets, new energy sources, a balance between chaos and calm, but the outskirts lean too far toward emptiness. And then comes the gravity problem. In the far outer regions, stars orbit the galaxy more loosely. Their paths are long and slow. They feel less influence from the central mass and more from the dark matter halo that surrounds the galaxy. These orbits can be stable, yes, but they can also be vulnerable to perturbations from other galaxies passing dwarfs or tidal forces. Over billions of years, these small disturbances can accumulate, slowly altering the orbits of stars and planets. A planet could drift slightly closer to its star or slightly farther away over immense time spans. Small changes can destabilize climates, freeze oceans, or evaporate atmospheres. The risk is subtle but real, especially in regions where stars have less gravitational support from the dense galactic disk. So we face a paradox. The outer galaxy is calm but too calm, safe but too safe, stable but starved of resources. It avoids the dangers of the core, but it also lacks the richness that fuels life. The truth becomes clearer when we compare it to our own position. Earth is not near the galactic center, but we are not near the outskirts either. We live in the middle zone where metallicity is high, star formation is modest, and evolutionary time can unfold peacefully. Our location is neither desperate nor dangerous. It is balanced, and balance is everything. The outskirts, in contrast, are cosmic deserts. Beautiful, quiet, and vast, but barren. A planet here may enjoy calm for billions of years, but it may never receive the ingredients needed for biology. It might remain a cold, lifeless world orbiting a star that sits alone in the darkness. Yet even deserts can hold surprises. There may be rare regions where metallicity is higher, remnants of past interactions, or small pockets enriched by wandering gas clouds. A lone world in the outskirts could still harbour oceans beneath ice. It could still host simple life in deep subsurface environments. The universe loves exceptions. But as a whole, when we look at the statistics, the outer regions of galaxies contribute very little to the overall chances of life. They are too poor, too thin, and too chemically simple for complexity to flourish. And that brings us to the centre of our search. If the core is deadly and the outskirts are barren, then life must rise in the middle. The galactic suburbs, the regions between chaos and emptiness, become the true incubators for biology. They offer radiation levels that are manageable. They offer metallicity that is sufficient. They offer orbits that are stable. They offer time, the most important ingredient of all. So let us now step into this middle zone, a place like our own cosmic neighbourhood, a place where the balance between danger and safety creates the perfect environment for life to begin. This is where our journey continues. Between the dangerous core of a galaxy and the cold emptiness of its outskirts lies a region that is neither chaotic nor barren. It is the middle zone, a broad belt of stars, gas and dust that circles the galaxy in quiet rotation. Astronomers often call it a moderate density region, but the name does not capture its importance. A better term is the galactic suburbs. And just like suburbs on Earth, these regions sit at a comfortable distance from the noise of the centre, and far enough from the isolation of the edge. They are calm, stable, and rich enough to build worlds. For life, they may be the most promising real estate in the entire universe. The galactic suburbs offer a raw balance. They contain enough heavy elements to form rocky planets. They avoid most of the radiation storms from the core. They have star formation that is active but not violent, and they maintain stable orbital patterns over billions of years. This balance is everything. Life, as far as we know, does not need perfection. It does not need a quiet universe or a flawless star. What it needs is time, long uninterrupted time in an environment that is neither too dangerous nor too empty. The suburbs of a galaxy offer exactly that. They provide an environment where stars can form, planets can cool, atmospheres can settle, and evolution can unfold without constant resets. Our sun is a perfect example of this. It lives about halfway between the Milky Way's centre and the edge. This location is not random. It is the result of billions of years of galactic evolution. At this distance, metallicity is high enough that the solar system could form rocky planets like Earth, Mars, and Venus. But the region is quiet enough that catastrophic events are rare. Supernovae happen but not nearby. Radiation flows through space but not in overwhelming levels. The black hole at the centre is far away. The outskirts are far away. The sun lives in the middle, the place where life has a chance. When we look at other spiral galaxies, we see similar structures. Andromeda has sprawling suburbs. The Triangulum galaxy has elegant, well-formed arms, where the environment mirrors our own. Even smaller spirals show the same pattern, a calm, moderate zone where conditions appear balanced and friendly. These regions tend to be rich in dust lanes. Dust may seem insignificant, but it is essential. Dust grains carry carbon compounds. They host complex molecules on their surfaces. They create planet-forming disks around newborn stars. Without dust, rocky planets would be rare. But in the suburbs, dust clouds stretch for thousands of light years, forming nurseries where stars and planets emerge together like seeds sprouting in fertile soil. Another important feature of the suburbs is orbital stability. Stars orbit the galaxy in long, slow curves. In the core, these orbits can be chaotic. In the outskirts, they can be loose and easily perturbed. But in the middle region, the gravitational pull is smooth and predictable. Stars maintain consistent paths for eons. This stability allows planetary systems to remain orderly for the deep time required for biology to advance. There is also a delicate balance in star formation. Too much star formation produces too many massive stars that die quickly in supernova, flooding the region with radiation. Too little star formation means there are not enough new planets being built. The suburbs sit between these extremes. They produce a healthy mix of star types, long-lived red dwarfs, sun-like stars, and even some larger ones, but not in numbers, that endanger everything around them. If we were to zoom into one of these suburban zones in a distant galaxy, we would likely see scenes that feel strangely familiar. Clusters of newborn stars glowing in pink nebulae, streams of dust weaving through spiral arms, calm wide regions filled with older stars that have not exploded in billions of years, and between them countless planetary systems quietly unfolding their histories. It is in these regions that life, if it exists in other galaxies, is most likely to begin. But this raises a deeper question. How common are these galactic suburbs? Are they rare, appearing only in galaxies like the Milky Way? Or are they a universal feature of spirals across the cosmos? The answer is encouraging. Most spiral galaxies appear to have broad, stable mid-regions. Even galaxies that look chaotic from afar may hide calm lanes within their arms. These suburban zones may stretch for thousands of light years and contain hundreds of billions of stars. If even a small fraction of those stars host rocky planets, then the number of potential life-bearing worlds becomes enormous. But spirals are not the only galaxies with potential. Elliptical galaxies, though older and quieter, may host habitable zones that are even more stable, lasting far longer than anything in a spiral. Their star formation may be nearly finished, but their stars are ancient and peaceful. The suburbs of an elliptical galaxy may be smaller, but they could be unimaginably old, and age gives life time. Still, stability alone is not enough. Life also depends on the overall distribution of stars across a galaxy. Even in the suburbs, some stars will be born in clusters too dense, and some will drift too close to dangerous regions. The environment is good, but not guaranteed. It is like living in a quiet neighborhood near a city usually peaceful, but occasionally affected by events far away. Yet when astronomers model galaxies statistically, one conclusion keeps appearing. The middle zones of galaxies offer the highest chance for life to emerge. Not the bright core, not the silent edge, but the wide balanced region between them. This insight reshapes how we think about life in the universe. It tells us that if we look for life in other galaxies, we should focus not on their centers or their outskirts, but on their vast invisible suburbs. It also leads us to the next step in our journey. If these suburbs are where life is most likely to begin, then how many stars actually form there? And how many of those stars have environments similar to the Sun? To answer that, we must zoom in again from galactic geography to the intimate spaces around individual stars and to the conditions that turn raw dust and gas into planets where life might take hold. That is where we go next. Before we can estimate the chances of life in other galaxies, we must return home for a moment. Not to Earth, but to the Milky Way itself, our reference point, our case study, our only known example of a galaxy that successfully produced life at least once. Everything we know, everything we guess, everything we model about life beyond our galaxy begins right here. And the first question is simple. How common are potentially habitable worlds inside the Milky Way? For most of human history, we had no answer. The night sky looked empty. Stars looked lonely. And Earth felt like an exception. But over the last 3 decades, that illusion has shattered. With telescopes like Kepler-T's Gaia and JWST astronomers have discovered that planets are not rare at all. They are everywhere. The Milky Way is not a desert sprinkled with a few oases. It is a vast archipelago of worlds, tens of billions of them. When astronomers study sun-like stars, nearly every one of them appears to have at least one planet. Many have multiple planets. Some have systems more crowded than ours. Others have orbits more stable. A few appear strangely Earth-like. And many live in regions of the Milky Way that sit comfortably inside the galactic suburbs. This alone reshapes our understanding. The Milky Way has roughly 400 billion stars. If even 10% of them have rocky planets located in their habitable zones, a conservative estimate, we may be looking at tens of billions of potentially Earth-like worlds in one galaxy. Of course, not all rocky planets are equal. Some orbit violent stars that flare too often. Some sit in unstable systems. Some have atmospheres that leak away. Some may have been sterilized by ancient supernovae. But the numbers are still enormous. Even if we filter by metallicity, star type, orbital stability, radiation exposure and age, billions of candidates still remain. Now consider the Milky Way's structure. The most promising region, our galactic suburbs, contains a large portion of the galaxy's sun-like stars. This region extends for thousands of light years and contains hundreds of billions of planets combined. Even if life is rare, the number of attempts becomes overwhelming. But the Milky Way is not uniform. Some regions are far more dangerous than others. Near the core, radiation levels spike. The number of supernovae increases. The gravitational chaos produced by tightly packed stars destabilizes planetary systems. Planets there may never get the stable conditions needed for life to evolve beyond microbes. In the outskirts, the opposite problem emerges. Metallicity drops. There are fewer heavy elements. There are fewer rocky planets. Even if life could exist on icy moons or subsurface oceans, the raw materials for Earth-like chemistry are scarce. So the Milky Way narrows the landscape. Not every star is promising. Not every region is suitable. Not every planet is stable. But even with all of these restrictions, the remaining number of habitable candidates is staggering. Astronomers also discovered something else. Life's basic ingredients form easily. Organic molecules, including complex carbon chains, appear in interstellar gas clouds. They form on the surfaces of dust grains. They survive supernova shocks. They float in comets. And they have been detected in star-forming regions all across the galaxy. This is important because it shows that biology is not limited by chemistry. The chemistry is already happening everywhere. What limits life is time stability and environment. When we combine all known data, the Milky Way presents itself as a galaxy where rocky planets are common, organic molecules are widespread, water is abundant, long-lived stars are numerous, and stable environments exist across broad regions. This makes the Milky Way a life-friendly galaxy. Not perfect, not safe in every corner, but rich in opportunities. And now comes the key point. The Milky Way is not special. Everything we see here, star formation, metallicity gradients, spiral structure, dusty suburbs, can be found in countless galaxies across the universe. If life can emerge here, then galaxies with similar structures should offer similar chances. But before we scale up to the entire universe, we need to look at something subtle: the distribution of stars within the Milky Way. Are most stars in stable regions? Do most stars form in places where rocky planets can survive? Or are we the exception, a lucky outlier in a galaxy full of danger? This matters deeply, because if our galaxy concentrates most of its stars in dangerous regions, then galaxies like the Milky Way might produce far less life than the raw number suggests. But if stable regions dominate, then the chances of life increase dramatically. So to understand the universe, we must first understand our home. Not Earth, not the solar system, but the galactic architecture that shaped both. Only then can we scale this knowledge to the billions of galaxies beyond each with its own possibilities. In the next part, we take that step outward. We go from one galaxy to all galaxies, and the numbers will surprise you. If the Milky Way were the only galaxy in the universe, our question would already be enormous. But the Milky Way is not alone. Far from it. It is just one member of a population so vast that language struggles to describe it. When we look deeper into the universe, past the nearby stars, past the faint glows of the local group, past the clusters and filaments of cosmic structure, we discover something staggering. The observable universe contains trillions of galaxies. Not millions, not billions, trillions. Each one is a self-contained island of stars, gas, dust, and dark matter. Each one carries its own history. Each one runs its own experiments with chemistry, time, and gravity, and each one offers its own chances or failures of life. What happens when we take what we know about the Milky Way and scale it upward? The first and most important insight is this: the Milky Way is typical. It is not the largest galaxy. It is not the smallest. It is not unusually rich in metals. It is not unusually poor. It does not form stars unusually fast or unusually slowly. It is average, and that is powerful, because if a typical galaxy can produce at least one biosphere, then typical galaxies everywhere might be doing the same. Let's start with the simplest comparison. Spiral galaxies like the Milky Way and Andromeda, make up a substantial portion of the universe's bright population. They have broad disks, active star formation, and metallicity patterns similar to ours. Nearly all of them contain rich reserves of gas and dust. Nearly all of them form stars steadily over billions of years. Nearly all of them have large calm mid-regions where stable planetary systems can exist. If even a small fraction of these spirals host habitable zones similar to ours, then the number of potential life-bearing worlds across spiral galaxies alone becomes immense. Tens of billions per galaxy, trillions across the universe. But the universe contains more than spirals. It contains elliptical galaxies which may be quieter but far older. These galaxies formed most of their stars long ago in ancient bursts that filled them with heavy elements. Their stars are stable. Their environments are calm. Their violent past lies behind them. If long-lived stability is the key to life, ellipticals may be prime candidates. They lack fresh star formation, but they offer an environment that could support life for astonishing spans of time. They're also irregular galaxies, twisted and chaotic, shaped by collisions and gravitational tides. On the surface, they look hostile, but even these galaxies contain pockets of stability. Dense clouds where new stars form, calm corners protected from chaos by geometry or timing. Life does not require perfection, it requires opportunity. And even irregular galaxies may contain enough opportunity for something to begin. Then there are dwarf galaxies, the smallest and most numerous galaxies in the universe. Many are low in metallicity. Many struggle with star formation. Many lose their heavy elements to supernova winds. But even dwarfs come in enormous numbers, far more than giants like the Milky Way. If even 1 in 1,000 dwarfs develops a small habitable region, the total number of habitable environments becomes huge. When astronomers model galaxy populations statistically, they find something profound. There is no single galaxy type that dominates the probability of life. Instead, every galaxy contributes differently. Spirals contribute size and chemical richness. Ellipticals contribute stability and age. Irregulars contribute diversity and complexity. Dwarfs contribute pure numbers. Together they create a universe filled with chances. Now let's apply a simple thought experiment. Suppose the Milky Way has a few billion potentially habitable worlds. That number alone is overwhelming. But now imagine that number applied to 1 trillion galaxies. Even if only 1 in 100 galaxies has conditions similar to the Milky Way, we still get tens of billions of galaxies capable of producing billions of habitable planets each. The scale becomes incomprehensible, even if life is rare, even if evolution to complex forms is unlikely, even if intelligence is extremely difficult. The sheer number of attempts makes it almost impossible for the universe to have succeeded only once. The universe has had 13.8 billion years to run its experiments. Galaxies formed early, stars formed early, planets formed early. And we know from observations of distant galaxies that the chemistry of life carbon compounds, water vapor. Complex molecules existed when the universe was a fraction of its current age. The raw ingredients have been present across cosmic time and cosmic space. So the question shifts. It is no longer could life exist in other galaxies. It becomes how could it not? But before we jump to conclusions, we must look deeper, because galaxies differ not only in structure but in their internal conditions. Some are bursting with star formation, producing radiation too intense for life. Some are quiet deserts. Some are violent. Some are peaceful. Some are haunted by past collisions. Some are ancient survivors. To truly understand the chances of life in other galaxies, we must compare these environments in detail. We must ask which types of galaxies produce the highest probability of life, which produce the lowest, and why. When we look at the universe through powerful telescopes, galaxies seem almost interchangeable. Spirals, ellipticals, dwarfs, glowing islands floating in darkness. But beneath their beauty, each galaxy has a distinct personality shaped by its history, its composition, and its internal physics. And these differences matter deeply when we ask the question at the heart of this journey. Where does life have the best chance to appear? The truth is simple. Not all galaxies offer the same opportunities. Some are fertile gardens. Some are barren deserts. Some are violent arenas where life is crushed again and again. And some are peaceful sanctuaries that could shelter biology for tens of billions of years. So let's explore these cosmic personalities one by one. Spiral galaxies, the cosmic cradles. Spiral galaxies like the Milky Way and Andromeda are among the most promising environments for life. Their elegant arms are rich in dust and gas. Their star formation is active but balanced. Their metallicity is high enough to build rocky planets. And most importantly, their vast galactic suburbs offer long-term stability. Spirals create stars steadily over billions of years. This slow but continuous pace allows new generations of planets to form, while older systems enjoy stability. It is a mix of renewal and calm, the ideal recipe for environments where biology can emerge, survive, and evolve. If life is common in the universe, spiral galaxies likely host a large fraction of it. Elliptical galaxies, ancient and quiet. Elliptical galaxies are different. They are smooth round and filled with older stars. They no longer form many new stars because they used up or lost their gas long ago. At first this might sound like bad news for life. No new stars, no new planets. But elliptical galaxies have something spirals do not: age. Their stars are ancient and stable. Their environments are calm and free of the violent star-forming regions that dominate younger galaxies. Many ellipticals have high metallicity from past generations of stars, meaning they may hold vast numbers of old rocky planets. Imagine a world billions of years older than Earth, orbiting a quiet, long-lived star in a peaceful corner of an elliptical galaxy. Life there could be unimaginably ancient, with a head start of billions of years. If complex life requires deep time, ellipticals might be silent treasure vaults filled with ancient biospheres. The challenge is that elliptical galaxies lack new star formation. The planets that exist there are relics of a distant past. If conditions were good early on but became harsh later, life may have struggled. Yet if these planets remain stable, the opportunities could be extraordinary. Irregular galaxies, chaotic but creative. Irregular galaxies break all the rules. They have no clear shape. Their gas clouds are twisted by tidal forces. Their star formation is uneven and sometimes violent. They are the cosmic equivalents of stormy weather, unpredictable, intense, and full of surprises. At first glance, these environments seem hostile. Bursts of star formation produce waves of radiation. Supernovae are common. Metallicity varies wildly from region to region. Many planets formed in these galaxies would face harsh, unstable conditions. But chaos is not the same as impossibility. Irregular galaxies often contain dense pockets of gas protected from violent regions. These pockets can quietly form stars with stable, long-lived planetary systems. And because irregular galaxies are often small, even a single safe pocket could represent a large fraction of the galaxy's habitable environments. Life needs stability, but stability does not have to be universal. A quiet corner in a chaotic galaxy might be enough. Dwarf galaxies small but numerous. Dwarf galaxies are the smallest galaxies in the universe, and they are also the most common. The majority are metal poor and prone to losing gas from supernova winds. Their ability to form rocky planets is limited. Star formation happens in bursts often triggered by gravitational interactions with larger galaxies. Still, their sheer numbers make them impossible to ignore. There may be hundreds of billions of dwarf galaxies in the observable universe, even if only 1 in 1,000 contains a pocket where metallicity is high enough for rocky planets. The total number of potentially habitable environments becomes enormous, and some dwarf galaxies, particularly those orbiting larger spirals, can acquire enriched gas from past interactions. These dwarfs may be small, but they can carry chemically rich material capable of forming Earth-like planets. Most dwarfs are poor candidates for life, but their numbers alone mean they still contribute meaningfully to the universe's total chances. Galaxy collisions dangerous but full of possibility. Galaxies collide more often than you might think. The Milky Way itself is on a collision course with Andromeda. These collisions are slow stretching over billions of years, but they completely reshape galaxies. During a collision, gas clouds compress, triggering intense star formation. Radiation levels rise. Many worlds become uninhabitable. But at the same time, collisions can mix gas reservoirs, increase metallicity, and create new regions where chemically rich stars and planets can form. Collisions are both destructive and creative. They erase possibilities while creating new ones. They reduce the habitability of some regions while enriching others. A universe with galaxy collisions is a universe where life's chances shift constantly. The cosmic patchwork. When we put all this together, a picture emerges. The universe is a patchwork of environments. Some galaxies are friendly, some are dangerous, some offer a small chance of life, some offer enormous potential. But the most remarkable insight is this: nearly every major type of galaxy offers at least some opportunity for life. Not in equal measure, not with equal probability, not with equal stability, but the ingredients for life, stars, planets, metals, and time appear everywhere, spread across billions of environments. The diversity of galaxies does not reduce the chances of life. It increases them. Thus, every type of galaxy contributes something different to the universe's probability of life. Spirals contribute numbers of stars. Ellipticals contribute time. Irregulars contribute variety. Dwarfs contribute abundance. And collisions contribute renewal. Life, if it exists beyond the Milky Way, must be shaped by this cosmic diversity. And now that we understand how different galaxies influence the chances for life, it is time to look at the galaxy not as a whole, but as a collection of stars. Stars that form live dye and enrich the universe with the seeds of biology. Because to grasp the true probabilities, we must now zoom down from galaxies to the stars themselves, and what they mean for life across the cosmos. When we look at the universe, we often want simple answers. Is there life out there or not? But the universe does not work in absolutes. It works in chances. It works in billions of small probabilities, repeating again and again across cosmic time. And when you see the universe through this lens, the question changes. It becomes less about whether life exists elsewhere and more about how many opportunities the universe has created for life to begin. To understand this, imagine a quiet framework, not a strict formula, but a way of thinking. Start with a single galaxy like the Milky Way. Inside it are billions of stars scattered across stable regions. Each star carries some chance of forming rocky planets. Each rocky planet carries some chance of holding water. Each watery world carries some chance of stabilizing its climate. And each stable climate carries some chance of beginning chemistry that could one day awaken life. At every step the chances decrease, but the number of attempts is enormous. Even small probabilities become powerful when multiplied across billions of stars. Now imagine scaling that idea outward. Millions of galaxies, billions of galaxies, trillions of galaxies. The universe begins to feel less like a silent void, and more like an engine constantly running life's experiment in countless places. Let's explore this probabilistic universe through simple ideas, each flowing into the next. Rocky worlds are common. Planets made of rock do not seem rare anymore. Telescopes have shown that stars with moderate or high metallicity form rocky planets often. The suburban regions of spirals are full of them. Many ellipticals have ancient rocky worlds forged in their early star-forming years. Even irregular galaxies, chaotic as they are, contain pockets where metallicity is high enough to form solid planets. Even if only a small percentage of Sun-like stars host Earth-sized planets, the total number across a large galaxy reaches the billions, and that is per galaxy. Water appears everywhere. Water is not a luxury. It is a result of simple chemistry. It appears in comets and nebulae, in young star systems, and in the atmospheres of planets we have only just discovered. The building blocks are universal. Hydrogen, the most common element in existence, and oxygen forged in stars and spread by supernovae. So the chance of water forming somewhere inside a planet-forming disk is very high. Galaxies across the universe share this behavior. Stability makes time possible. Life does not need perfect conditions, but it does need time. Galactic structure creates a natural filter. The core is too chaotic. The outskirts are too empty. But the middle, the quiet, stable lanes last for billions of years. Many spiral galaxies have these zones. Many ellipticals have them as well. Where stability exists, possibility exists. And each stable region contains millions of stars. Chemistry happens automatically. Organic molecules form on dust grains. They float in clouds. They drift between stars. They condense inside comets. The universe does not need life to begin chemistry. The chemistry does that on its own. This means that many planets start with the ingredients life requires. Life is not limited by raw materials. It is limited by environment and time. Life itself is the big unknown. Here is where uncertainty enters. We know life began on Earth early. Very early. That hints that life may begin quickly when conditions are right. But we cannot be sure. Maybe the universe favors life. Maybe life is incredibly rare. But the probability alone does not matter. What matters is the scale. Even if the chance of life forming on a suitable planet is tiny, far smaller than we expect, the total number of suitable planets is vast. Billions per galaxy multiplied across trillions of galaxies. The universe has tried the experiment countless times. Small chances, large numbers, long time scales. Together they create possibilities that are almost impossible to dismiss. Complexity is even harder. Simple life may begin easily. Complex life takes far longer. Earth needed billions of years to take that step. Many planets will not have that luxury. Some will be struck by disasters. Others will freeze or overheat. Many will fail. But the universe is generous with attempts. Even if complex life emerges on a tiny fraction of planets, the total number could still be immense. Intelligence is the deepest mystery. Intelligence may be common. It may be rare. It may require a chain of lucky evolutionary pressures. Or it may arise naturally when complexity reaches a certain threshold. We simply do not know, but the probabilistic universe does not require intelligence to be common. It only requires that it is possible and that the universe is old and large enough to allow the attempt. And it is the cosmic average. When we combine everything, rocky planets, water, stability, chemistry, complex evolution, one truth emerges. The universe does not need high probabilities for life to appear. It only needs enough chances, and galaxies provide those chances in staggering numbers. Each galaxy is a factory producing stars and planets. Some factories are efficient, some are quiet, some are chaotic, some are ancient. But together across time and space they generate a universe where life is not a miracle. It is a statistical expectation. Life does not require a perfect universe. It requires a large one, and ours is larger than anything we can fully imagine. In the next part, we bring all these probabilities together and ask a deeper question. How do galaxies with their different personalities shape the long-term fates of worlds that may hold life? If the universe is probabilistic, then galaxies become the stage where probability turns into possibility. But not all stages are equal. Some galaxies nurture life gently, others crush the smallest spark. Some offer stability for billions of years. Others rewrite themselves violently before life has any chance to grow. So what makes a galaxy life-friendly? What separates a cosmic cradle from a cosmic desert? To answer this, we must look beyond individual stars and individual planets. We must see the galaxy as a system, a living ecosystem in its own right, shaped by its structure, history, and internal rhythms. A life-friendly galaxy is not simply one with stars and planets. It is a galaxy where the environment stays kind long enough for life to rise, adapt, and evolve. Let's explore what that truly means. Long-term stability is essential. Life needs time. Not millions of years, billions. Earth required nearly 4 billion years to move from the first simple cells to complex organisms. That long timeline demands a galaxy that behaves consistently. A galaxy cannot bombard its planets with constant radiation. It cannot collapse its star-forming regions too quickly. It cannot swing wildly between violent and quiet phases. Spiral galaxies tend to perform well here. Their rotation, their structure, and their spread-out star formation create long-lasting calm zones. Elliptical galaxies may be even better, ancient steady objects that have not changed dramatically for billions of years. Stability is the first ingredient of a life-friendly galaxy. A steady supply of heavy elements. Life-friendly galaxies must contain enough carbon, oxygen, nitrogen, iron, silicon, and phosphorus to build rocky planets and to fuel complex chemistry. These elements are forged in stars and released in supernovae. Galaxies that form many generations of stars build up large stores of heavy elements over time. Spirals excel at this because they maintain star formation for billions of years. Ellipticals excel because they formed huge numbers of stars early on. Some irregulars also produce enriched regions thanks to past interactions. Dwarfs, however, often struggle. Their shallow gravitational wells let metals escape easily. They are not lifeless by definition, but they are less fertile. Heavy elements are the second ingredient of a life-friendly galaxy. Moderate star formation, not too fast, not too slow. Star formation drives evolution, but it also creates danger. Too much star formation means too many massive stars, and massive stars explode violently. A galaxy that constantly detonates supernovae is not safe for long-term survival. Radiation waves sweep through the galaxy. Atmospheres get stripped. Chemistry is damaged. But too little star formation means the galaxy stops renewing itself. Its gas cools. Its dust disperses. Its supply of planets freezes in time. Life-friendly galaxies sit between these extremes. They form stars steadily and calmly, not in bursts, not in droughts. This gentle pacing keeps environments enriched without drowning them in danger. A calm influence from the central black hole. Nearly every galaxy has a supermassive black hole at its heart. Some are quiet, like the one in the Milky Way. Others blaze with energy-consuming matter and releasing colossal jets that sterilize entire regions. A galaxy hosting an active black hole, a quasar, becomes a dangerous place. Radiation floods across vast distances. Gas clouds are heated. Star formation is disrupted. Whole sectors become uninhabitable. Life-friendly galaxies tend to have quiet, well-behaved black holes. They sit calmly. They do not erupt often. They allow the galaxy around them to stay peaceful for long stretches of time. This central black hole does not have to be small, only quiet. A balanced structure. The physical layout of a galaxy matters. A galaxy with smooth rotation avoids chaotic gravitational disturbances. A galaxy with gentle metallicity gradients supports rocky planets across wide regions. A galaxy with broad spiral arms or smooth elliptical profiles offers many safe pockets. Structure creates predictability, and predictability allows life to unfold. Spiral galaxies provide a beautiful example. Their arms are not rigid structures. They are density waves, gentle sweeping lanes where star formation begins and ends in rhythmic cycles. These patterns create large stretches of moderate habitable territory. Ellipticals offer a different kind of stability. No arms, no bursts, just long-lived stars glowing softly across ancient time. Two different paths, one shared benefit. Calm. A history without too many collisions. Galaxy collisions are spectacular. They tear gas clouds apart. They trigger massive starbursts. They reshape entire structures. But they also bring chaos. Radiation rises. Orbits shift. Gas gets compressed or expelled. A life-friendly galaxy can survive one or two collisions in its deep past, perhaps even benefit from the enrichment. But a galaxy that collides frequently becomes turbulent for billions of years. Life needs a galaxy that has been mostly left alone. A gentle spread of stars. In a life-friendly galaxy, stars are not packed too tightly. They are not flung too far apart. They move through space with calm gravitational guidance. Their orbits remain stable. Their environments stay predictable. Planets do not get yanked off course or irradiated by passing giants. The Milky Way's suburbs show this perfectly. Stars are close enough to share resources, yet far enough to avoid harming each other. It is the cosmic version of a peaceful neighborhood, bringing it together. When all of these conditions combine, stability, heavy elements, gentle star formation, a quiet black hole balanced structure, a stable history and well-spaced stars, the result is a galaxy where life has room to breathe, a galaxy where biology can begin, where complexity can rise, where intelligence given enough time might emerge. And here is the most inspiring truth. Many galaxies in the universe meet these conditions. Not all of them, not even most of them, but enough of them to make the universe feel alive with possibility. In the next part, we take one step deeper and explore how stars themselves, their lifetimes, their temperaments, and their environments shape the story of life across galaxies. To understand life in other galaxies, we must zoom in from the grand scale of spirals and ellipticals to something far more intimate, the stars themselves. Because every planet, every ocean, every climate, every spark of biology depends on the nature of the star it orbits. A galaxy may provide the environment, but stars provide the stage where life actually unfolds. And across the universe, stars come in extraordinary variety. Some burn fiercely and die young. Some glow steadily for trillions of years. Some drift in calm neighborhoods. Others rage in clusters filled with radiation. Not all stars offer the same chance for life. In fact, the type of star a planet orbits may matter more than the galaxy it lives in. Let's explore how stars shape the cosmic odds. Long-lived stars create opportunity. Life requires time, deep stretches of time. Stars that burn quickly cannot offer this. Massive stars, for example, shine intensely but die fast. Some live only a few million years before exploding as supernovae. Even if a planet formed around such a star, it would be destroyed long before life had a chance to begin. This is why long-lived stars dominate our expectations. Small stable stars, especially orange dwarfs and red dwarfs, can burn for tens of billions or even trillions of years. They provide gentle warmth and steady light. They do not erupt often. They evolve slowly. They offer conditions that can last far longer than the entire lifetime of our Sun. These stars are everywhere, and because they are small, they are also numerous, making up the majority of stars in most galaxies. If the universe hosts widespread life, many of those worlds may orbit tiny suns glowing softly for cosmic ages. But long-lived stars come with challenges. Red dwarfs, the most common stars in the universe, live incredibly long lives. But they also tend to flare. Some release bursts of radiation that can strip atmospheres or damage early chemistry. Not all red dwarfs behave this way, but many do, especially young ones. So while red dwarfs create immense opportunities, they also introduce uncertainty. Their planets may succeed, or they may fail. The outcome depends on timing distance and atmospheric resilience. This adds complexity to the universal equation. Not all long-lived stars are ideal, but many may still support life. Sun-like stars offer stability and balance. Stars like the Sun represent a middle ground. They burn brightly but steadily. They produce moderate radiation. They live long enough for complex life to evolve. They avoid extreme flaring. They sit in the sweet spot between intensity and longevity. Sun-like stars may not last as long as orange or red dwarfs, but they offer stable conditions for billions of years, enough time for evolution to work slowly and patiently, as it did on Earth. Galaxies that produce large populations of sun-like stars become strong candidates in the search for life. The Milky Way is one of them, and so are many spirals across the universe. Star clusters, beauty and danger. Some stars are born in clusters, tight radiant concentrations of hundreds or thousands of newborn suns. They glow beautifully in telescope images wrapped in pink gas and shimmering dust. But clusters are dangerous places. Stars sit close together. Radiation is intense. Massive stars explode early and often. Gravitational disturbances twist the orbits of planets. Most planets born in clusters do not remain stable long enough for life to evolve. They are ejected or destabilized. They are bathed in radiation. They lose their atmospheres. Star clusters are breathtaking, but for life they are short-lived and harsh. Stars in quiet regions are the best candidates. Life-friendly stars tend to form not in clusters but in calmer regions. Small associations that drift apart slowly, or isolated pockets of star formation, where stars emerge with enough breathing room to evolve peacefully. These quiet births often occur in the suburban lanes of galaxies. Here dust clouds collapse gradually. Star-forming regions are large but not dense. Supernovae are rare but still provide enrichment. Planets form without constant interference. If the Milky Way had to choose where its life-bearing star would be born, it could hardly choose better than the calm region where the Sun formed. Metallicity determines planet formation. Metallicity. The abundance of heavy elements in a star plays a critical role in shaping planetary systems. Stars with higher metallicity produce more rocky planets. Stars with lower metallicity produce fewer. This means that stars born in metal-rich suburbs of galaxies are more likely to host worlds like Earth, while stars in metal-poor outskirts or primitive dwarf galaxies may form gas giants instead. Across the universe, metallicity varies from galaxy to galaxy and from region to region. But the overall trend is clear. Where metallicity is moderate to high Earth-like planets are common. Spiral galaxies lead in this category. Ellipticals provide ancient enriched material. Even some irregulars host pockets where metals accumulate. Stars with the right chemistry greatly increase the odds of life. Galactic history shapes star populations. A galaxy's past determines its star populations. Galaxies that formed many stars early on tend to have older, stable stellar populations, ideal for slow, steady evolution. Galaxies with recent bursts of star formation produce more hostile environments filled with massive stars and frequent supernovae. This is why elliptical galaxies, though quiet, may host countless ancient worlds, and why spirals, though active, may host new opportunities continuously. Each galaxy writes a different story for its stars. Each population brings its own set of possibilities. Stars are the true engines of probability. Galaxies set the stage, but stars determine the story. Every star is a roll of the cosmic dice. Some rolls produce barren ice worlds. Some produce scorching gas giants. Some produce rocky planets in perfect orbits. Some produce life. Multiply these rolls by hundreds of billions of stars per galaxy, and then by trillions of galaxies, and the probabilistic universe becomes clear. Life does not need to be common. It only needs to be possible. Stars ensure that possibility repeats again and again everywhere. And now that we've explored how stars shape life's chances, the next step brings us even closer. We move from stars to planets, to worlds themselves, to the landscapes where life may rise in quiet oceans, hidden valleys, distant atmospheres, or deep subsurface seas. To understand life beyond our galaxy, we must focus on the true stage where everything begins. Not the galaxy, not the star, but the planet. A silent sphere of rock or ice or gas. A world shaped by heat, gravity, chemistry, and time. A world where environments rise and fade, where climates stabilize or collapse, where water collects or disappears. Planets are where probabilities become realities. They are where the cosmic story touches the surface. And across the universe, planets exist in astonishing variety. Some are frozen moons drifting around faint stars. Some are massive super-Earths with crushing gravity. Some are scorching worlds where metals melt into rivers. Some are ocean planets with no land at all. Some carry atmospheres thicker than entire oceans. Some have none. Each of these worlds carries its own potential. Each holds a different answer to the question of life. Rocky worlds, the foundations of complexity. When astronomers search for life, they often begin by searching for worlds like Earth, small rocky planets with solid surfaces. This is not because Earth is the only path to life. It is because rocky worlds offer something unique, a place for chemistry to settle. On a rocky planet, molecules can form in oceans, mix in rivers, interact with minerals, and become part of cycles. Volcanic activity provides heat and nutrients. Plate tectonics recycle materials. Weather shapes landscapes. Rocky planets are laboratories for complexity, and the universe forms them everywhere. Spiral galaxies produce them steadily. Ellipticals may host ancient rocky planets from early epochs. Even irregulars hold pockets where rocky worlds can arise. Where metallicity is moderate to high, rocky worlds are almost unavoidable. Water, a universal solvent. Water is one of the most powerful ingredients for life. Not because it is magical, but because it allows chemistry to move freely. It dissolves compounds, it transports nutrients, it stabilizes temperatures, and water is abundant. We see it in comets. We see it in star-forming regions. We see it in the atmospheres of exoplanets. We see it in the icy moons of our own solar system. This means countless planets across the universe likely carry some form of water. Oceans, ice layers, vapor clouds, subsurface seas. A planet does not need continents to host life. It only needs liquid water somewhere. Ocean planets, icy moons with internal heating, and worlds with deep underground seas may all support chemistry that evolves slowly in the dark. In many galaxies, these water-rich worlds may be far more common than Earth-like twins. Atmospheres, shields and engines. A planet's atmosphere is its protection. It blocks harmful radiation. It traps heat. It allows climates to form. It circulates nutrients and gases. But atmospheres are fragile. They can be stripped by stellar winds. destroyed by nearby supernovae, evaporated by flares from young stars, frozen by distance or lost to space. Some planets hold their atmospheres for billions of years. Others lose them in their infancy. The survival of an atmosphere is one of the key factors that determines whether a planet can sustain life, and this survival depends on many elements: the planet's gravity, the activity of its star, its magnetic field, its distance from radiation sources, its early history. A galaxy filled with calm, stable stars increases the number of planets capable of maintaining atmospheres long enough for life to begin. The habitable zone, a moving target. We often talk about the habitable zone, the distance from a star where liquid water can exist. But this zone is not fixed. It changes over time as stars age and grow brighter. Young stars may have narrow habitable zones. Older stars have wider ones. Some stars shift so slowly that their zones remain stable for billions of years. A planet does not simply need to be in the habitable zone. It must stay in the habitable zone. That requires long-term orbital stability and a star that evolves gently. Galaxies with large populations of calm, long-lived stars naturally produce more worlds that meet this requirement. Worlds beneath ice. Hidden possibilities. Some of the most promising worlds in the universe may not be rocky planets like Earth. They may be icy moons orbiting giant planets, worlds with frozen surfaces but warm oceans underneath. These oceans are heated not by sunlight, but by tidal forces, radioactive decay, or internal chemistry. Europa Enceladus Titan. Our own solar system provides examples that hint at a broader truth. Life may thrive even in places where starlight barely reaches. Across galaxies, icy moons may be far more common than Earth-sized worlds in habitable zones. If life can exist in these underwater oceans, the number of potential biospheres increases dramatically. Galaxies with rich moon-forming environments, especially spirals with active planet formation, may host millions of subsurface ocean worlds, super-Earths and mini-Neptunes. Not all rocky worlds are Earth-sized. Some are larger with thick atmospheres and strong gravity. Some are smaller with thin atmospheres that leak easily. Super-Earths may have stable climates and long-lived geological activity, perfect conditions for life. Mini-Neptunes might hide oceans beneath thick atmospheres. Their surfaces may be unreachable, but their internal oceans could host chemistry. A life-friendly galaxy is one that produces a wide variety of these planets. Big, small, dense, airy. Because diversity increases the chances that at least some will be suitable for biology. Planetary systems, order and chaos. Finally, we must consider the architecture of planetary systems. Some systems are stable with planets in calm orbits. Others are chaotic with giants migrating inward, scattering smaller worlds. Galaxies with smooth star formation and balanced metallicity tend to produce more orderly systems, the kind that give planets time to evolve. In contrast, galaxies with violent histories may produce systems in constant flux. The more stable the environment of star and gas clouds, the more likely a galaxy is to spawn planets that remain in place long enough for life to appear. Worlds are the true carriers of life's story. Galaxies set the structure. Stars set the conditions. But planets carry the narrative. On their surfaces or beneath their oceans or inside their atmospheres, chemistry begins, changes, adapts, and branches into countless possibilities. The universe may be full of planets that never develop life, but it may also be full of worlds where chemistry has been simmering for billions of years, quietly exploring the pathways that lead from molecules to biology. Now that we understand planets themselves, the next step is clear. We must explore how life begins, the fragile spark, the first chemistry, and the conditions that turn raw matter into metabolism. Life does not begin with planets or stars or galaxies. It begins with chemistry. Quiet, fragile, persistent chemistry, unfolding on a world that is stable enough, warm enough, and wet enough for long stretches of time. Every living thing, no matter how complex, descends from a moment when simple molecules first organize themselves into something that could change, adapt, and reproduce. That moment is the most delicate step in the cosmic story. It is the thin bridge between a silent planet and a living one. To understand the chances of life in other galaxies, we must understand this bridge. And it begins with the ingredients. Ingredients form easily. Across the universe, the building blocks of biology appear everywhere. They form in cold molecular clouds. They cling to dust grains. They drift through nebulae. They are delivered to newborn planets in icy comets. Astronomers have detected amino acids in meteorites, organic molecules in distant star-forming regions, and complex carbon chains in environments so extreme that humans once believed nothing interesting could exist there. This tells us something profound. The early chemistry of life does not require a miracle. It only requires the right combinations of atoms, carbon, hydrogen, nitrogen, oxygen, interacting in environments where energy is present. Galaxies provide those environments endlessly. Energy drives the first steps. Life cannot begin without energy. Energy fuels reactions, builds molecules, and drives complexity. But not all energy is equal. Gentle, steady energy helps molecules assemble. Violent bursts destroy them. On young planets, energy comes from many sources. Starlight warms oceans. Lightning activates chemical pathways. Volcanic vents pump out heat and minerals. Tidal forces need internal oceans on icy moons. Radioactive decay warms underground environments. These are universal processes. Any planet with water and heat becomes a laboratory, where chemistry experiments run continuously for millions of years. Given enough time, simple molecules form chains. Chains fold. Folded molecules become catalysts. Catalysts lead to replication. Life's spark is not a single moment. It is a slow dance of chemistry reaching towards structure. Stability allows chemistry to mature. A planet must remain stable long enough for chemistry to take hold. No violent sterilization. No runaway freezing. No atmosphere lost too quickly. No surface blasted clean by nearby supernovae. This is where galaxies matter again. A planet near a calm star in a calm region has deep time to build complexity slowly. Galaxies with broad suburban zones offer the best chance. Stars there evolve gently. Radiation stays moderate. Planets keep their atmospheres. Oceans stay liquid for eons. If the first spark needs hundreds of millions of years, galaxies with stable regions are essential. Multiple pathways to life. We often imagine life beginning the way it did on Earth, in warm oceans beneath a young sun, but galaxies allow a diversity of pathways, in subsurface oceans beneath ice, in hydrothermal vents, in chemical gradients deep underground, even in thick atmospheres where droplets form temporary microenvironments. Life may not require continents or sunlight. It may not require Earth-like landscapes at all. If a world has liquid water, available chemistry, and a steady source of energy, it has a chance. And such worlds exist across many galaxies. Chemistry is persistent. If life does not begin once, it may begin again. If conditions fail in one region, they may succeed in another. If a spark fades, another may rise centuries later. Planets do not host chemistry for a moment. They host chemistry for geological ages. Tides continue. Volcanoes continue. Atmospheres circulate. Molecules bump into one another endlessly. The universe does not try once. It tries repeatedly. In galaxies full of rocky planets and icy moons, the conditions for life's beginning repeat over and over across billions of worlds. Life's spark does not require perfection. Earth's early environment was far from gentle. Meteor impacts, volcanic eruptions, harsh ultraviolet radiation, intense storms, and yet life appeared quickly, astonishingly quickly, once the surface stabilized. This suggests something important. Life does not require a peaceful paradise. It requires endurance. It requires opportunity. It requires time. Every galaxy with calm regions and water-rich planets provides those opportunities. A universal pattern emerges. When we combine everything we know, ingredients, energy, stability, chemistry, A pattern begins to take shape. Life begins where water is present, molecules can assemble, energy flows gently, environments remain stable for long periods, chemistry runs unhindered. These conditions do not depend on one galaxy. They do not depend on one star. They do not depend on one rare chain of events. They are universal. They appear in spirals, ellipticals, and many irregulars. They appear around sun-like stars, orange dwarfs, and even some red dwarfs. They appear on rocky worlds, icy moons, and deep underground seas. Life's spark may be delicate, but the universe provides countless chances for it to awaken. The first step is only the beginning. The origin of life is the smallest chapter in the story. What comes after stability evolutions, complexity requires far more time and far more favourable conditions. Some worlds will fail early, some will survive longer, some will develop only simple chemistry, some may reach the threshold of biology, and others given billions of years may climb toward complexity. Now that we understand how life begins, the next question is natural. How often does simple life survive long enough to evolve into something more, and what environments allow complexity to flourish instead of collapse? Life's beginning is fragile, but its survival is even more delicate. Chemistry may produce simple cells, but turning those cells into a stable biosphere requires a planet that protects them long enough for evolution to work. The universe may spark life frequently, but only some environments allow that spark to grow into something durable. So where does simple life survive, and what shapes its fate across galaxies? To answer that, we need to look at the conditions that keep early life alive, not for a moment, but for geological ages. Survival depends on calm periods, not perfect ones. Simple life does not require a flawless world. It does not need continents, seasons, or oxygen-rich skies. Early life on Earth thrived in oceans filled with volcanic minerals and low oxygen levels. Conditions were harsh, yet life survived. What mattered was not perfection, but persistence. Long periods without global sterilization, energy sources that did not disappear, chemistry that could continue uninterrupted. This means simple life may survive on many worlds that look hostile to us. If a planet offers pockets of stability, deep oceans, underground caverns, hydrothermal vents, early life can endure even if the surface is chaotic. Across galaxies, such stable pockets exist in enormous numbers. Water shields and nourishes. Water protects life. It absorbs radiation. It stabilizes temperatures. It stores heat. It dissolves nutrients. Simple life often thrives in water-rich environments where temperature swings are small and chemistry remains active. Oceans, lakes, and subsurface seas become natural refuges, so planets or moons with liquid water even below ice are strong candidates for sustaining early life. Icy moons in particular may be ideal. Their oceans are shielded from radiation by kilometers of ice. They receive steady heating from tidal forces. Their chemistry continues even when the surface above is frozen solid. Galaxies filled with such worlds hold vast potential for long-lasting simple life. Atmospheres. Fragile but powerful. An atmosphere helps life survive, but it is also vulnerable. Young stars flare. Supernovae blast shock waves across space. Galactic radiation levels rise and fall. If an atmosphere is stripped away too early, the surface becomes barren. If it is too thick, heat may trap and boil oceans. If it is too thin, the world may freeze. Simple life can survive without a perfect atmosphere, especially in oceans, but worlds with stable atmospheres have an enormous advantage. Galaxies with calm mid-regions tend to produce stars that allow atmospheres to stay intact for billions of years. This stability directly increases the survival chances for early biology. Energy needs to be steady, not violent. Life needs energy, but not explosions. Not flares. Not catastrophic shifts. Early Earth life relied on gentle, continuous energy sources. Sunlight filtered through shallow oceans. Geothermal heat from the crust. Chemical gradients near vents. Tidal heating in some environments. These sources are available across many galaxies. Even the faintest stars provide steady warmth. Even the smallest moons experience tidal forces. Even the quietest worlds contain radioactive elements that heat their interiors. This means simple life does not rely solely on starlight. It may thrive in darkness heated from within. A universe with billions of rocky planets and even more icy moons becomes a universe rich in hidden habitats. Microbial life is resilient. Microbes endure extremes that humans cannot imagine. They survive intense radiation. They survive freezing temperatures. They survive boiling water. They survive high-pressure toxic chemistry and long global winters. Life at this level is adaptable. It spreads. It hides. It waits. It endures planetary catastrophes that would wipe out complex ecosystems instantly. This resilience is important for galaxies filled with messy environments. Even in regions where stars flare or conditions fluctuate, microbial life may survive underground or underwater, continuing quietly for billions of years. Galaxies do not need perfect order to support simple life. They only need regions where endurance is possible. Extinction events are common but not always total. Planets experience disasters, impacts, volcanic eruptions, global warming events, ice ages, radiation bursts, but microbial life can survive these cycles. On Earth, life endured asteroid impacts, supervolcanoes, atmospheric collapses and ice ages that froze continents. After each event, the simplest cells repopulated ecosystems quickly. This suggests that early life may survive even when planets face periodic setbacks. Complete sterilization is rare. Local destruction is common. Recovery is likely, and across billions of planets, many worlds will avoid the worst disasters entirely. Galactic environments shape survival rates. Simple life may arise frequently across a galaxy, but its survival depends on the region. Core regions are too violent. Outskirts may lack energy or warmth. Middle regions, the galactic suburbs, offer the highest chances. Here, radiation levels are moderate. Atmospheres remain stable. Stars flare less. Water stays liquid. Chemistry continues for geologic ages. Large galaxies offer more of this space. Small galaxies offer less. But almost every galaxy type contains some stable zones, and where stability exists, survival becomes likely. Simple life may be the most common form in the universe. If we follow the logic, ingredients are common. Water is common. Energy is common. Rocky worlds are common. Icy worlds are common. And microbial resilience is high. Then the conclusion becomes unavoidable. Simple life may be widespread across galaxies. These worlds may not host forests or animals or continents, but they may host oceans where chemistry has been simmering for billions of years, hidden, slow, quiet, but alive. In spirals, in ellipticals, in irregulars, in dwarfs, in ancient worlds orbiting quiet stars, in young planets developing chemistry today. Life may survive in countless forms across space. But the next question is far more challenging. How often does simple life take the next step? How often does it grow more complex instead of remaining microbial forever? Simple life may survive easily across the universe. But complex life with tissues, organs, movement, intelligence, behavior is far more demanding. It requires a world that remains calm for immense stretches of time. It requires stable climates, rich chemistry and energy sources that do not vanish overnight. Most of all, it requires a planet that is not interrupted too often by global catastrophes. If simple life is like a spark, then complex life is a slow-growing flame. It needs protection. It needs patience. It needs billions of years. So where and how does complex life arise? Complexity requires time. On Earth, life appeared early, but complexity took almost 4 billion years to evolve. 4 billion years of stable oceans, stable energy, and stable chemistry. 4 billion years without complete sterilization. 4 billion years of evolution uninterrupted by cosmic disasters. This tells us something crucial. Complex life is not fast. It is slow. It is patient. It requires stability on unimaginable timescales. Galaxies that offer long-lived calm regions, especially spirals and ellipticals, become the strongest candidates for hosting complex ecosystems. Stable climates create evolutionary pressure. Complex life needs an environment where natural selection can build, not too chaotic, not too uniform, a world that challenges organisms gently, not violently. Planets with stable oceans, moderate geological activity, and steady climates create this kind of environment. Seasonal changes shape adaptation. Coastal zones encourage diversification. Ecosystems emerge where sunlight, nutrients, and shelter mix in the right ways. Across galaxies, the planets most likely to develop complexity are those with long-lasting oceans, continents or varied surfaces, moderate climate cycles, stable atmospheres, reliable energy from their stars. These conditions can exist on many worlds, not just Earth-like ones. Even ocean planets or thick atmosphere worlds could develop complex life if their environments remain stable. Energy availability determines complexity. Complex organisms require more energy than microbial ones. They need oxygen or an equivalent oxidizer. They need sunlight or chemical gradients. They need ecosystems with food webs. Energy-rich planets, those with active geology, open oceans, and significant atmosphere, provide these gradients. On Earth, the rise of oxygen transformed the planet from a microbial world into a place capable of supporting animals, plants, and eventually intelligence. Other planets may follow different chemical pathways, but they still require a large, consistent source of energy to fuel complexity. This does not limit complex life to Earth-like atmospheres. It simply requires a stable chemical gradient, something galaxies create repeatedly across millions of worlds. Catastrophes must be moderate, not extreme. Catastrophic events can halt complexity or push it forward. Small disasters encourage adaptation. Large disasters reset the evolutionary clock. A world struck too often by supernova radiation or massive impacts may never progress beyond microbial life. But a world with moderate stress, periodic ice ages, volcanic episodes, shifting climates may evolve rapidly. Galaxies with calm mid-regions naturally produce more planets with moderate, not extreme catastrophe rates. These worlds have time for ecosystems to rise, diversify, collapse, and rise again. A cycle that fuels complexity. Tectonics and geology shape habitability. Geological activity is crucial. It recycles nutrients. It creates coastlines. It fuels deep ocean ecosystems. It builds varied terrain. It regulates atmospheric gases. Planets that are geologically alive offer more niches for evolution to explore. Galaxies with high metallicity produce more rocky planets with radioactive heating, increasing the likelihood of tectonics. This means spirals and enriched ellipticals may contain more planets capable of supporting complex biospheres. Icy moons may host their own pathways. Complex life may not be limited to surface oceans. Some icy moons contain deep internal oceans that are stable for billions of years, heated by tidal forces. Life there would evolve without sunlight, in total darkness under enormous pressure. It might never build civilizations, but it could build complexity ecosystems built around vents, rich networks of organisms adapted to chemical gradients instead of sunlight. These kinds of worlds may be incredibly common across many galaxies. Wherever giant planets form icy moons, follow. Wherever icy moons form deep oceans, follow. Wherever deep oceans exist, chemistry endures. The probability space grows wider, not narrower. Complex life may be far less rare than we think. We often imagine complex life as a rare accident because Earth's history seems long and unlikely. But from a cosmic viewpoint, Earth is only one sample. The universe may contain ancient worlds older than Earth, stable planets orbiting quiet stars, ocean planets with deep, safe environments, enriched rocky worlds in metal-rich galaxies, super-Earths with thick atmospheres and warm seas. Each one provides opportunities for complexity to rise. Even if only 1 in 1,000 or 1 in a million microbial worlds becomes complex, the sheer number of worlds ensures that millions of complex ecosystems could exist across the observable universe. But complexity is not the final step. Complex life may thrive on many worlds, but intelligence, the ability to use tools, communicate abstractly, and reshape environments, requires an even more delicate balance. It needs stability energy, long evolutionary pathways, and the absence of repeated global resets. So even if simple life is common, and even if complex life is widespread, intelligence might be rare, or it might not be rare at all. The only way to understand intelligence in a cosmic context is to explore how often evolution produces it, and what environments make it possible. That brings us to the next part, the journey from complexity to consciousness, and the galaxies most likely to host intelligent life. Complex life may flourish across the universe on countless worlds, but intelligence, the ability to observe, analyze, communicate, and reshape the environment, is a very different step. It is the deepest evolutionary leap life can take. It requires a rare blend of biological potential, environmental stability, and long-term opportunity. Intelligence is not guaranteed. It is not the natural endpoint of evolution. It is one of many possible paths, a path that may emerge only under unusual conditions. So what allows a world to cross this final threshold? Intelligence requires stability on immense timescales. Animals, plants, and ecosystems can rise in a few 100 million years. But intelligence requires much longer periods without complete ecological resets. A single gamma ray burst a nearby supernova, a massive impact, or a runaway global freeze can delay evolution by tens or hundreds of millions of years. Earth's history shows this clearly. Several mass extinctions almost erased the lineages that eventually produced intelligent species. If any sterilizing event has been slightly stronger, the outcome could have been completely different. This means intelligence demands a world where large-scale extinction events occur, but not too often, and not too catastrophically. The environment must challenge life, but not destroy it. Galaxies with calm metal-rich regions provide such environments more frequently than chaotic galaxies or dwarf galaxies. Energy-rich ecosystems encourage cognitive development. Brains are expensive. They consume enormous amounts of energy. They require stable food webs and reliable nutrient cycles. Only planets with rich ecosystems can sustain species with advanced cognition. Dense forests, abundant oceans, warm climates, and varied landscapes give evolution the raw material needed to explore complex behaviors. Predation, cooperation, tool use, and social structures arise only when ecosystems are diverse and competitive. This is why intelligence is more likely to emerge on planets with stable climates, long coastlines and varied terrains, nutrient-rich oceans, moderate geological activity, steady energy from their stars. Such planets exist wherever galaxies produce well-balanced rocky worlds. Environmental pressure shapes minds. Evolution does not create intelligence for its own sake. It creates intelligence when the environment rewards it. Life becomes smarter when navigating terrain becomes beneficial. Communicating improves survival. Cooperation increases fitness. Tool use leads to advantage. Memory and planning help species adapt. These pressures develop in worlds that offer both challenges and opportunities. Not too harsh, not too simple a middle ground where thinking provides meaningful benefit. Planets lacking environmental diversity may never produce intelligence even if complex life thrives, but planets with forests, oceans, mountains, seasons, predators, prey, and cycles of scarcity often push evolution toward more flexible minds. Across galaxies, such worlds may be far more common than we imagine. Large brains need long lives. Species that evolve intelligence usually live long enough to benefit from learning. Long lifespans allow knowledge to accumulate between generations. Social structures protect individuals during vulnerable years. Memory becomes useful only when organisms have time to use it. On Earth, many intelligent species, dolphins, elephants, primates, ravens, live long lives and care for their young. This pattern may be universal. Long-lived animals are more common around stable stars and in moderate ecosystems. Galaxies with large populations of calm stars produce more worlds where such species can emerge. Social behavior accelerates intelligence. Social species face complex challenges that solitary species do not. They must communicate, negotiate, cooperate, compete, remember alliances, interpret signals, and predict behavior. These pressures shape advanced cognition. Intelligence may therefore be more likely to evolve in species that hunt cooperatively, raise offspring collectively, defend territories in groups, migrate seasonally, develop communication systems. Planets with stable climates and abundant habitats naturally support social species. Galaxies with many such planets support more paths to intelligence. Intelligence is a product of rare conditions, but the universe has time. Even if intelligence is rare, extremely rare, the universe has had billions of years and trillions of planets to try. If only 1 in a billion planets produces an intelligent species, the observable universe could still host millions of civilizations across cosmic time. Most may have risen and fallen long before humanity existed. Some may rise long after we're gone. Some may exist now scattered across galaxies in environments where evolution took a similar long winding path. Galaxies with calm mid-regions, long-lived stars, stable planetary systems, rich ecosystems, are the best candidates for hosting intelligent life. Intelligence is not the final step, communication is. A species may be intelligent yet isolated. Many intelligent species on Earth never develop complex tools, written language, or advanced communication. They experience the world deeply but do not reshape it. For intelligence to affect the galaxy, one more step is required: the emergence of technological civilization. This step may be even rarer. It may require fire, dexterous limbs, stable climates, cooperative societies, and long-term cultural continuity. But somewhere in the universe these conditions likely appear many times across billions of years. The question then becomes, how often does intelligence become civilization? How often does consciousness reshape a world so profoundly that it begins to reach for the stars? Intelligence alone does not create civilization. The universe may be full of intelligent species creatures that think, communicate, form social bonds, and navigate complex environments. But civilization requires something more. It demands a convergence of biology, environment, and opportunity that is far rarer than intelligence itself. Civilization is not just a brain. It is a brain paired with tools, cooperation, communication, and stability strong enough for knowledge to accumulate across generations. This transition from intelligent life to technological civilization is one of the rarest and most delicate leaps in the cosmos. So what shapes this threshold? Civilization requires manipulative ability. A species may be intelligent, but if it cannot shape its environment, it cannot build technology. Tool use requires anatomy that allows precision. Hands, tentacles, flexible limbs, or specialized appendages could all serve this purpose. On Earth, many intelligent species lack the ability to manipulate objects precisely. Dolphins communicate richly but cannot craft tools. Elephants understand complex ideas but do not build structures. Ravens use tools but cannot construct advanced technology. This means that even if intelligence is common, civilization may be limited to species with fine motor control, flexible limbs, grasping appendages, coordinated movement, problem-solving linked to tool use. Galaxies with diverse ecosystems are more likely to produce such species. Fire or an equivalent energy source. The development of technology requires controlled energy. On Earth, fire was the catalyst. It allowed early humans to cook produce, heat craft materials, and eventually smelt metals. Other civilizations may rely on different energy sources, chemical reactions, geothermal vents, or even biological electricity. But some form of controlled accessible power source is essential. Worlds that are too wet, too cold, or too oxygen poor may host intelligent species that never cross this threshold. Without stable energy sources, technology cannot advance. Galaxies with many Earth-like planets or planets with varied biomes will produce more opportunities for technological breakthroughs, stable climate for long-term development. A civilization cannot form if climate catastrophes erase progress repeatedly. It needs long stretches of environmental moderate stability, centuries, even millennia, to accumulate knowledge, build cities, domesticate resources, and pass on culture. Planets with gentle seasons, moderate geological activity, stable coastlines, predictable weather patterns, provide ideal environments where civilizations can flourish. Galaxies with calm mid-regions produce more planets that meet these criteria, increasing the probability of technological evolution, social cooperation, and cultural memory. Civilizations arise when intelligent organisms work together. Social species develop shared goals, collective learning, communication, and memory systems. They create language, rituals, tools, knowledge storage, cooperation across generations. Without cooperation, intelligence remains isolated. But with cooperation, knowledge grows exponentially. Galaxies that host planets with rich ecosystems encouraging interdependence among species may produce more social animals capable of large-scale coordination. Geographical diversity encourages innovation. A world made entirely of ocean or ice or desert may support life, even intelligent life, but civilization requires diversity. Coastlines that encourage trade, mountains that create barriers, rivers that encourage exploration, varied climates that demand adaptation, landscapes that offer materials like metals, wood, stone, clay, or minerals. This geographical variation encourages problem-solving and resource development. A planet with extremes and transitions stimulates creativity. Worlds with balanced geology and active tectonics are more likely to produce complex civilizations, and such worlds are common in metal-rich galaxies. Abundant resources enable technological growth. Civilizations require access to key resources, metals, minerals, combustible materials, usable energy sources, stable food supplies. Metal-rich galaxies naturally produce planets with more accessible resources, and thus more potential for advanced technology. Galaxies poor in heavy elements may host intelligent species that never enter an industrial stage simply because they lack materials. Communication expands civilizational scale. Long-distance communication is the moment when a civilization becomes more than a collection of isolated groups. Language, writing symbols, and eventually electronic communication bind individuals into a larger whole. Technological civilizations unify multiple regions of their planet, share knowledge globally, and accelerate development rapidly. Planets with stable atmospheres and varied landscapes produce the strongest foundation for communication networks. Civilization may rise many times and fall many times. Across the universe, countless intelligent species may rise just short of civilization. Some may achieve early stages of tool use but collapse due to climate shifts. Others may build simple structures but never reach metallurgy. Some may develop advanced societies but be destroyed by catastrophes. Civilization is a narrow path, a delicate balance of opportunity and restraint. But the universe is vast. Even if only a tiny fraction of intelligent species form civilizations, the total number across trillions of galaxies could be enormous. Millions of civilizations may have existed throughout cosmic history. Some still exist now. Some may rise in the future. Some may fall before they ever leave their home worlds. The critical step: becoming a spacefaring species. Civilization alone does not guarantee longevity. The universe is dangerous. Asteroid impacts, supervolcanoes, climate collapse, and stellar evolution threaten long-term survival. A civilization that remains confined to a single planet may eventually disappear, but a civilization that becomes spacefaring acquires resilience. It spreads, it adapts, It survives events that would destroy a single world. The next part explores this final evolutionary step, how civilizations cross the boundary from local to cosmic, and how galaxies shape their destiny among the stars. Civilizations begin small, a single species on a single world surrounded by uncertainties and limited by the boundaries of its environment. But once a civilization gains the ability to reach beyond its home planet, everything changes. The universe becomes larger, opportunities multiply, and survival becomes more likely. The transition from planetary civilization to spacefaring civilization is one of the most dramatic steps life can take. It shifts the fate of an entire species from vulnerable to resilient, from temporary to potentially long-lived. But how often does this transformation occur across the universe? And what determines whether a civilization becomes cosmic or collapses before leaving its home? Spaceflight, a narrow window of opportunity. A civilization must develop the knowledge, technology, and stability required for spaceflight before internal or external threats overwhelm it. This window may last tens of thousands of years, a blink on cosmic timescales. During this period, a civilization must navigate environmental challenges, resource limitations, geopolitical tensions, technological risks, planetary hazards. Many civilizations may advance scientifically, yet never reach space halted by catastrophe or internal instability. Galaxies with safer mid-regions offer more planets where civilizations have time to overcome these challenges. Energy determines expansion. Leaving a planet requires immense energy. Crossing a solar system requires more. Crossing star systems requires orders of magnitude more. Civilizations must access stable, high-density energy sources, fusion antimatter or advanced reactors, long before they can expand significantly. Galaxies rich in heavy elements provide more opportunities for energy availability. Galaxies with long-lived stars give civilizations more time to develop such technologies. Colonization requires stability and motivation. A civilization may have the technology to reach other worlds, but it also needs the motivation to do so. Expansion requires a stable societal structure, long-term planning, cooperation on planetary scales, scientific curiosity, the ability to invest resources far beyond immediate needs. Civilizations undergoing constant conflict, environmental collapse, or resource scarcity may lack the unity or stability to colonize space. Galaxies with calm, mature star populations may host more civilizations capable of sustained long-term planning. The first steps beyond the home planet. The earlier stages of cosmic expansion are modest. A civilization begins by building orbital habitats, mining asteroids, establishing research stations, exploring moons and near planets. These initial steps transform planetary civilizations into multi-world civilizations. Even a small presence in space significantly improves survival chances. A single asteroid impact or volcanic eruption can no longer end a species' future. Across galaxies, any civilization that reaches this level becomes statistically more likely to endure. Interstellar expansion, slow but powerful. Crossing between stars is slow even for advanced civilizations. But speed is not the limiting factor, persistence is. If a civilization launches slow-generation ships, self-replicating probes, or robotic explorers, it can spread steadily even if each jump takes centuries. Given millions of years, a patient civilization could fill an entire galaxy with outposts, habitats, and artificial ecosystems. Galaxies with calm, stellar neighborhoods and abundant habitable worlds become fertile ground for such expansion. Galactic structure shapes civilizational destiny. The layout of a galaxy matters. Spiral galaxies have orderly rotation and large habitable zones. Civilizations in these regions may spread along the spiral arms, gradually populating star systems at a manageable pace. Elliptical galaxies with huge numbers of ancient, long-lived stars may host civilizations that began billions of years before humanity existed. Their calmer environments and stable stellar populations could allow uninterrupted expansion across vast distances. Irregular galaxies may be harder to navigate, but they are not impossible. Civilizations there may adapt to chaotic star patterns and unpredictable movement. Every galaxy provides unique pathways for expansion. Civilizations must survive their own technology. The greatest threat to any civilization may be itself. Advanced technology brings immense power: nuclear weapons, engineered diseases, uncontrolled artificial intelligence, climate modification, resource depletion. A civilization must learn to balance technological capability with wisdom. Those that fail may disappear before reaching the stars. Those that succeed may achieve stability that lasts for tens of thousands of generations. Galaxies with stable environments give civilizations time to develop the social maturity needed to survive this critical phase. Cosmic hazards still exist. Even spacefaring civilizations face danger. Supernovae, gamma-ray bursts, rogue planets, asteroid clusters, shifting galactic environments. But the more worlds a civilization inhabits, the more resilient it becomes. A multi-system or multi-armed civilization can endure catastrophes that would destroy a single world. Galaxies with wide, safe regions offer more room for civilizations to spread and diversify. The potential for immortality. A civilization that expands across thousands of star systems becomes difficult to extinguish. Local disasters can no longer end its existence. Knowledge can be preserved across vast distances. Multiple cultures, technologies, and habitats emerge. Even if parts of the civilization collapse, other branches continue. This redundancy gives rise to cosmic longevity. Such civilizations may have existed long before Earth formed. Some may exist now hidden by distance. Others may rise in the future given the right conditions. The universe is old enough and wide enough for many such destinies. But not all civilizations explore. Some civilizations may turn inward, choosing philosophy, virtual existence, or sustainable planetary life rather than expansion. Others may plateau technologically. Some may lose interest in exploration, especially if their environments provide everything they need. Life's path is not singular. Civilizations may be diverse, unpredictable, and shaped by unique cultural choices. The next question, the galactic silence. If civilizations can rise and spread, if galaxies contain billions of potentially habitable worlds, if intelligence and technology are not impossibly rare, then why is the universe so quiet? Why have we not detected signal structures or traces of other civilizations? This brings us to one of the deepest mysteries in astronomy, the Fermi paradox, the cosmic silence that shapes our understanding of life among the galaxies. We have explored stars, planets, chemistry, simple life complex, life intelligence, and civilizations. Each step seems rare, yet none feels impossibly rare. With trillions of galaxies, trillions of stars in each and untold numbers of planets, the universe should be filled with life. Not just simple organisms, but civilizations, some older than ours by millions or even billions of years. And yet across this immense cosmic stage we hear nothing. No signals, no beacons, no structures visible across intergalactic space, no hints of neighbours among the stars. This is the great silence, the deepest mystery of modern astronomy. If life is likely and intelligence is possible, why does the universe appear so quiet? The scale of the silence. The distances between galaxies are vast. Even the nearest galaxy, Andromeda, is more than 2 million light-years away. Any signal crossing that gap fades, distorts and disappears into cosmic noise. Even a powerful beacon would struggle to reach us before dissolving into the background. So the silence we observe may not mean emptiness. It may simply reflect the size of the universe. Signals weaken. Species rise and fall. Light takes too long to travel. Civilizations may exist but be separated by time as much as distance. We may be looking at a universe filled with life whose voices can never reach us. The timing problem. Even if civilizations are common, their windows of visibility may be brief. A civilization might broadcast for 1,000 years. Maybe 10,000, maybe 1 million. But on cosmic scales this is nothing. Galaxies evolve over billions of years, stars live for trillions. Civilizations may flicker into existence, rise, fall, and vanish long before their signals cross the void. Others may be born long after we disappear. We may simply not overlap. We may exist at the wrong moment in cosmic history, too early to hear ancient civilizations, too early for emerging civilizations, trapped in a universe where communication rarely aligns. Barriers to growth. Even if intelligent species arise, often the transition to civilization is fragile. Many potential civilizations fall before they ever send a single message. Some collapse due to environmental pressure. Some fail after technological missteps. Some are destroyed by natural disasters. Some never leave their home planet. Across galaxies, countless intelligent species may have lived and died without ever building a single transmitter. Many worlds may host minds that never become civilizations. Barriers to longevity. Civilizations must also survive themselves. Technological societies face risks that natural environments never created. Weapons capable of global destruction, engineered pandemics, ecological collapse, resource depletion, runaway technologies. The same intelligence that builds civilization can also end it. Civilizations may be bright but brief enough that their sparkle never reaches other galaxies. This possibility forms one version of the Great Filter, a barrier that few survive. Galactic hazards. Even if a civilization overcomes internal threats, the galaxy itself poses dangers. Supernovae, gamma-ray bursts, rogue planets, solar flares, chaotic orbits. Some galaxies are simply too volatile. Others have quiet regions, but not all civilizations arise in those safe zones. Many may be wiped out early by cosmic events before they ever look outward. A galaxy may nurture life for 1 billion years only to erase it with a single stellar explosion. The filter may be behind us or ahead of us. The Great Filter could be early. The origin of life, the jump to complex cells, the emergence of intelligence, the creation of civilization. If those steps are extremely rare, then we may already have passed the hardest parts. We may be one of the few species in the universe to reach this level. But the filter could also be ahead. Long-term survival, interstellar expansion, balancing technology with stability. If the hardest step is still coming, then the universe's silence may reflect the fate of countless civilizations that did not survive long enough to spread. We do not know which possibility is true. Civilizations may choose silence. Some civilizations may simply decide not to broadcast. They may hide to avoid danger. They may lose interest. They may turn inward, choosing virtual realities or controlled environments over expansion. In such worlds, communication with other galaxies is unnecessary, a curiosity rather than a priority. The silence may be cultural, not physical. Signals fade and structures disappear. Even if civilizations broadcast, the universe erases their presence over time. Stars move. Galaxies drift. Tidal forces distort structures. Cosmic dust absorbs light. Technological artifacts decay. A civilization's monuments may last millions of years, but galaxies last trillions. Anything left behind eventually fades into the background. We may be searching for signs in a universe that wipes itself clean. The universe may be filled with life, just not visible life. All these obstacles combine into a single truth. Civilizations may be plentiful across the universe, yet nearly impossible to detect. They may be separated by distance, time, culture hazard, or biology. They may whisper softly while cosmic noise roars. They may broadcast in ways we do not recognize. Life may be common. Civilization may be rare. And detectable civilization rarer still. The great silence may not reflect a lonely universe. It may reflect a universe too large, too old, and too quiet for voices to cross the void. But silence does not mean emptiness. Our next part asks a deeper question. If the universe is full of hidden civilizations, what traces might they leave behind, and how could we detect them among the stars? If civilizations exist across the universe, then somewhere in the darkness traces of their presence must remain. Light heat structures, signals, or engineered worlds, fragments of intelligence echoing across space. The cosmos does not hide energy. Anything that transforms starlight, moves planets, or violates natural patterns should leave a mark. So why have we not seen any? To answer this, we must explore the subtle signs that advanced civilizations might produce, and the reasons those signs remain invisible to us. The search for technosignatures. Astronomers search for unusual patterns in starlight and radio waves, patterns that cannot be explained by natural processes. These include heat signatures from massive structures, narrowband radio emissions, unnatural light pulses, changes in star brightness too regular to be natural, chemical imbalances in planetary atmospheres, signals that repeat with purpose. Any of these could reveal intelligence. Yet so far the universe remains quiet. But quiet does not mean empty. Megastructures, engineering on galactic scales. A sufficiently advanced civilization might build structures that harness its star's energy. One concept is a vast swarm of orbiting collectors that absorb starlight and radiate heat. If such a structure existed, its star would dim in visible light and glow strongly in infrared. Astronomers search for such anomalies. So far, none have been confirmed. But galaxies contain trillions of stars. We have examined only a tiny fraction. Large structures may also orbit planets, moons, or even black holes. They might appear as unusual shadow sharp periodic dips in brightness, or heat signatures unlike anything produced by nature. But distance weakens these signals. Dust obscures them, time blurs them. A megastructure built 1 million years ago may no longer exist today. Artifacts lost in immense distances. Imagine a technological civilization in a galaxy 50 million light-years away. Even if it built vast stations or fleets of craft, the light from those structures would be too faint to reach us clearly. The distance alone erases the detail. We do not lack intelligence. We lack proximity. Our tools are powerful, but galaxies are too large and intergalactic space too empty for small structures to leave clear fingerprints. The signs may be there, but hidden by the scale of the cosmos. Signals fade faster than civilizations rise. Radio signals disperse. Laser pulses diverge. Light dilutes across distance. Even the most powerful transmission fades into cosmic noise after traveling a few million light-years. A civilization might broadcast for 10,000 years. But between galaxies, 10,000 years is only a tiny whisper in a vast ocean of silence. Two civilizations may signal. Both may be active. Both may be advanced. And neither will ever hear the other. Civilizations may communicate in ways we cannot detect. Radio waves may be primitive to advanced species. They may use neutrino beams, gravitational wave modulation, quantum communication, or methods that rely on physics we have not yet discovered. To them, our listening methods may appear like trying to detect a conversation by watching shadows on a wall. If we are listening with the wrong tools, the silence becomes inevitable. Technosignatures may blend with natural phenomena. Some civilizations might alter their planets or stars subtly, not with dramatic megastructures, but with changes indistinguishable from nature. Atmospheric engineering, energy harvesting hidden within natural spectra, habitats built underground or underwater, data stored in low-energy mediums invisible to us. Their presence might look like natural variability, dust patterns, or thermal fluctuations. Without knowing what to look for, we may walk past countless signs without recognizing them. The universe can hide intelligence in plain sight. The universe erases evidence over time. Time is the ultimate destroyer of artifacts. Orbital structures decay. Megastructures disassemble. Technology rusts, melts, or collapses. Civilizations vanish. Even massive constructs may last only a few million years short compared to the age of galaxies. By the time their light reaches us, the civilization that built them may be long gone. We may be observing a universe after civilizations have flickered out, leaving only faint traces blurred by cosmic time. We have only just begun searching. Humanity has scanned only a microscopic fraction of the night sky. One star here, one planet there, a few wavelengths, a few decades of listening. The silence we hear may not come from absence, but from our short attention span. The universe is vast. We are new. Our tools are young. Somewhere among the billions of galaxies, techno-signatures may exist waiting for instruments far more powerful than today's telescopes. The darkness may not be empty. It may simply be too quiet for now. Our final part explores what this means not just scientifically, but philosophically, and how our existence fits into a cosmos that might be full of unseen life. The universe is ancient, older than life on Earth, older than our sun, older than every civilization that has ever existed on our world. Life intelligence and civilizations may rise and fall endlessly across cosmic history. Some may thrive in ancient galaxies, others may bloom in galaxies still forming stars today. Most will never meet. Most will never hear one another, but together they form a tapestry scattered, silent, but alive. A living cosmos is not a cosmos filled with voices. It is a cosmos filled with possibility. Life continues as long as stars shine. Stars will continue forming for trillions of years. Long after our sun dies, red dwarfs will still glow. Long after galaxies collide and merge, new planetary systems will arise. Life may begin again and again in environments that do not even exist yet. The universe is not done creating worlds. It is not done creating opportunities. Life may be in its early chapters, not its final ones. Galaxies shape the future of life. As galaxies merge and evolve, their environments change. Metal-rich regions spread. Calm stellar neighborhoods expand. New stars form from old gas enriched by countless past generations. Future galaxies may be even more life-friendly than today's. More planets, more water, more stable stars, more environments where biology can flourish. The potential for life does not shrink with time. It grows. Civilizations may seed the future. If spacefaring civilizations survive long enough, they may spread to other star systems carrying life with them. They may terraform barren worlds, warm frozen moons, or create artificial habitats in deep space. A civilization does not need to conquer the galaxy to influence it. It only needs to endure. Even a few resilient civilizations could shape the destiny of life for millions of years. Perhaps some already have. Perhaps some will in the distant future. The universe may be full of invisible stories. Civilizations may rise quietly, thrive for a time, and fade into memory long before their light reaches us. Others may expand across thousands of systems and leave no trace detectable from Earth. We may live in a universe filled with stories too distant, too faint, or too ancient for us to perceive, yet their existence still matters. They show that life is not a solitary miracle. It is a fundamental expression of cosmic evolution, our place in this vast story. Humanity is young, barely one heartbeat in cosmic time. We are the newest voice in a universe that has been whispering for billions of years, but our youth gives us potential. We can explore, we can search, we can listen, we can shape our future rather than wait for fate. If life is common, we are part of a vast cosmic family. If life is rare, then our existence becomes even more precious, a responsibility to preserve, protect, and extend. Either way, the universe becomes more meaningful, not less. A closing reflection. When we look up, we see darkness. But darkness is not emptiness. It is filled with unlit worlds, unborn stars, and unseen oceans. It is filled with chemistry waiting for its chance. It is filled with futures not yet written. We are one galaxy, one star, one world, one species. Yet we are part of a cosmos that may host life everywhere. Simple, complex, intelligent, or ancient beyond imagination. The silence we hear is not the silence of loneliness. It is the silence of distance, the silence of time, the silence of a universe too vast for easy connection. But hidden within that silence is possibility. And possibility is the first ingredient of life. Our journey is only beginning, and the cosmos vast, ancient, and full of potential waits quietly for us to explore it.